Space may feel endless, but in reality, we live in a very specific corner of the universe. A tiny pocket inside a thin spiral arm, drifting through a bubble carved by ancient explosions, wrapped inside a magnetic shield stretched thin across billions of kilometers. Around us, stars glide past over millions of years. When we look up, it is easy to think those stars are decorations pinned to a ceiling. But some of them are close enough that we can measure their light flicker across alien worlds. Some are calm, gentle suns. Others spit flares strong enough to peel atmospheres. A few hide planets we can barely detect. And one day, we may send probes there, riding beams of light or patient engines that burn for decades. Our place in the galactic web. It feels natural to think of Earth as the center of everything, because for most of history, that is all we could see. A blue world, a warm sun, and a night sky filled with lights that looked close enough to touch. Only when we learned to step back did we discover the truth. We are not the center. We are a single spark inside a vast city of suns, spread across a structure so wide and complex that even light needs tens of thousands of years to cross it. Our sun is one star among hundreds of billions. It shines in the Orion arm, a smaller lane between two grand spirals called Sagittarius and Perseus. Picture a glowing wheel spinning in space, like a giant pinwheel made of dust and fire. The Milky Way stretches more than 100,000 light-years wide, yet our solar system fills a space no bigger than a grain of dust on a map that size. And still, this dust grain is our whole world. We float here, moving around the center of the galaxy like passengers riding a slow and quiet train, circling once every 200 million years. Around us, the galaxy lives and breathes. Clouds of gas stretch like rivers in the dark, forming stars in slow bursts that take millions of years. Some regions shine like cosmic cities full of bright young suns. Others sit dim and silent, where stars have burned through their fuel and died long ago. Between these places, dark matter forms a hidden frame, a silent skeleton holding everything together. We cannot see it, and yet it shapes the motion of the stars and the curve of the galaxy. Without it, this great spinning disk might fly apart like dust in the wind. If the Milky Way is a city, then our solar system rests in one of its quiet neighborhoods. Not too close to the crowded core, where radiation can tear worlds apart and stars bump and tug at each other. Not too far from the outer edge, where heavy elements are rare and planets like Earth may never form. Here, at the right distance from danger and chaos, stars have time to settle and life has room to grow. Astronomers sometimes call this a Goldilocks zone on a galactic scale. In a universe full of storms and collisions, we found a peaceful place to build a home. Yet even in this calm region, space is not empty. The nearest stars sit just a few light years away, tiny sparks that move with us through the spiral arm. Some carry planets of their own. Some have disks of dust that may one day become new worlds. We drift side by side, a loose family of suns wandering in a slow dance shaped by gravity. From Earth, the Milky Way appears as a pale band stretching across the sky. It looks quiet and peaceful, like a soft cloud made of light. In truth, it is full of chaos and creation. Stars are born and stars explode. Black holes feast on gas and glow with fierce power. Planets form, crash and melt, then cool again into new shapes. Our place in this great wheel is humble, but not small in meaning. We are a witness to it. We are a part of it. The Sun orbits the center of the galaxy at a speed faster than any rocket humans have built. Yet the journey is so long that no living thing on Earth will ever see us complete a full loop. Dinosaurs once walked on Earth when we were in a different part of the Milky Way. Entire species rise and fall, entire ages pass, and the galaxy keeps turning. It does not hurry, it does not slow down. It simply moves with the deep patience of the universe. Look deeper still, and the structure around us becomes even grander. The Milky Way sits inside a cluster of dozens of galaxies, a family known as the Local Group. Our closest neighbor, Andromeda, rushes toward us through the dark. One day, billions of years from now, it will merge with us in a slow cosmic dance. Beyond the local group lies a vast thread of galaxies, like beads on a string. These threads fill the universe, weaving a structure we call the cosmic web. At this scale, galaxies become dust and clusters become grains, all arranged by gravity into shapes too large for our minds to fully grasp. Stand on Earth and look up. It is tempting to feel small, and in a way, we are. Our planet is a speck. Our sun is a spark. Our place in the Milky Way is a modest address. But this smallness reminds us that we come from something vast and that there is so much left to learn. To know our place is not to feel lost. It is to feel connected. Drifting through the Orion spur. When we look up at the night sky, many of the stars we see belong to the Orion spur. They are not scattered at random. They are neighbors along the same path, forming patterns that have guided humans for thousands of years. The familiar belt of Orion, the bright glow of Sirius, the gentle shine of the Pleiades. These are markers on our cosmic street, signs in a sky full of stories. They light our nights and remind us that we are part of a structure far bigger than our tiny blue planet. The Orion spur stretches across thousands of light years, thick enough to carry giant clouds of gas where stars are born. In this spur sits the Orion Nebula, a glowing nursery where new suns are forming right now. It hangs like a misty jewel below Orion's belt, and though it looks small to our eyes, it is massive beyond imagination. Inside it, young stars flare awake and planets grow from disks of dust, just as our own solar system once did. It is a window into our past. Other bright landmarks live here too. The Horsehead Nebula, shaped like a shadowy head rising from glowing gas. The Rosette Nebula, a wide bloom of pink and purple scattered petals of starlight. The Lagoon Nebula, swirling like a cosmic ocean storm frozen in time. These places are far away, yet they watch over us from the same spiral branch, sharing our road through the galaxy. If we could sail through the Orion spur, we would pass young star clusters shining like lanterns in the dark. We would drift through calm space dotted with lonely stars, and then arrive at dusty clouds thick enough to hide stars inside them. We would watch newborn suns break free, glowing stronger each day until they join the crowd and light their own planets. Our part of the spur is especially calm. Stars here are not too packed together. They keep their distance, moving like slow travelers on a wide road. Each follows its own orbit around the galaxy, shaped by gravity and time. Our sun is one such traveler. It drifts along with a loose group of stars called the local arm, though the name sometimes changes as astronomers refine their maps. Whatever we call it, this is home. A small stream in a grand cosmic river. Even though we share this spur with famous sites, most of it is too vast for us to ever fully explore. Light takes years to cross the emptiness between stars, and distances stretch beyond any journey we know how to take. Yet, we map it from afar with telescopes that catch faint colors and radio waves. We trace its shape like sailors charting a coastline they have never touched. Piece by piece, the picture grows clearer, and we see that our spur is not just a path. It is a bridge between great arms, a link in the galaxy's spiral dance. Inside this spur, stars vary in age and size. Some are small and steady like our sun. Others burn huge and hot, shining bright but living short lives before bursting apart. When those giants explode, they send shockwaves through space that stir clouds and spark new stars. This cycle keeps going, slow and steady, shaping the spur over millions of years. We are watching a living process, a quiet heartbeat of the Milky Way. This slow motion is our gift. Life on Earth needed peace and stability to take root. It needed sunlight that did not flicker, skies that did not boil with radiation, and a home star that wandered gently instead of crashing through dangerous zones. The Orion spur has offered that calm, not perfectly silent, but quiet enough for life to climb from simple cells to thinking beings who now ask where we came from. Stars will be born here long after our sun fades. Some of those worlds may one day host life of their own. Perhaps, far in the future, someone else will look up at their sky and see a band of light stretching across their night, never knowing that ours once did the same. They too will live in this lane of stars, drifting through a galaxy that will have changed but not disappeared. When we think about our place in space, it can feel overwhelming. Yet here, in this spur, we find comfort. We are not lost in chaos or trapped in emptiness. We are part of a gentle flow. It is calm enough to let life breathe, rich enough to build worlds, and lit by some of the most stunning sights in the night sky. The quiet drift of the solar system through space. Our solar system glides through space at breathtaking speed. The sun pulls us along as it travels, and we orbit with it, held tight by gravity like passengers aboard a great vessel. If we could watch from far outside the galaxy, we would see our solar system tracing a long curve through the Milky Way, sweeping around the galaxy's center in a huge, steady arc. We move at roughly 200 kilometers every second. In the time it takes to blink, we have traveled farther than any jet on Earth ever could. Yet we do not feel a thing, because everything near us moves together. The planets, their moons, the comets at the edge of our system all share this journey. To understand this, think about riding in a smooth airplane. When the plane moves at a steady speed, you feel calm, almost like you are not moving at all. A cup of water on your tray does not spill. A loose pen does not slide across your seat. Only when the plane changes direction or speed do you feel the motion. Space is like that too, only on a scale so large that our minds struggle to keep up. We are in motion, but we move so smoothly and so constantly that our senses are blind to it. The sun itself is following a path shaped by the mass of billions of stars and the unseen pull of dark matter. As previously mentioned, it circles the heart of the Milky Way roughly once every 200 million years. That means Earth has made only a few trips around the galaxy in its entire history. Our path is not a perfect circle. It wobbles up and down through the Milky Way's disk like a ship rising and falling on gentle waves. Sometimes we cross crowded regions filled with stars and dust. Sometimes we pass through quieter space. These shifts happen over millions of years, and they shape the environment around us. During busy periods, we may encounter thicker clouds of gas, or pass closer to other stars. During quiet ones, we sail through emptier space, leaving the nebulae and clusters behind like distant shores. Even smaller bodies within our solar system race along with us. Earth rockets around the sun at nearly 30 kilometers each second. That means we travel millions of kilometers each day without noticing. The moon orbits us as we orbit the sun, making a looping path through space like a ribbon trailing a dancer. Comets at the system's icy edge drift slowly, yet they too share the journey, bound to the sun by gravity's invisible thread. Other stars sweep near and far, each with its own path. Some move with us, part of the same stream. Others cut across our course like boats passing in the night. Over long spans, stars drift apart, and new neighbors take their place. Constellations will not always look the way they do now. The sky is a slow river of light, and we are floating in it. As our solar system plows through the interstellar gas, it carves a bubble called the heliosphere around us. This bubble shields our planets from much of the galaxy's harsh radiation, like a ship's hull protects travelers from waves. At its edge, where the solar wind slows and meets the pressures of the wider galaxy, lies a boundary like a shore, a place where the sun's influence fades and interstellar space begins. We crossed one such invisible border when the Voyager spacecraft reached the outer sea beyond our system. Those tiny machines left the comfort of the sun's bubble and announced that even out there, in far space, motion continues. Over millions of years, this steady drifting shapes our fate. As we travel, we may enter regions where gravity nudges long frozen comets toward the inner solar system. These icy wanderers could streak toward the sun, sometimes harmless, sometimes bringing change. Rarely, a close pass by another star might disturb the farthest reaches of our system. It has happened before and will happen again, but such events are rare and unfold slowly, over spans longer than human history. Through all of this, Earth rotates day by day, while circling the Sun in its patient loop. We build cities, discover new things, tell stories and live ordinary lives, unaware that we are part of a journey across the galaxy. If you stood on a mountaintop and looked at the horizon, the world would seem calm. But if you could see the truth hidden behind the peaceful sky, you would see that nothing ever rests. Without motion, stars would not form. Without motion, galaxies would not spin. Without motion, we would not exist. The local interstellar neighborhood and the local interstellar cloud. Around our Sun lies a gentle stretch of space, often called the local interstellar neighborhood. It sounds like an empty place, a quiet gap between stars. But like a small town at night, silence does not mean nothing is there. This space is full of thin gases, drifting dust grains, faint magnetic fields and stars. Our Sun sits inside a warm region of thin gas called the local bubble. Think of it as a wide clearing carved out by ancient stars that once exploded. Millions of years ago, giant stars in this part of the galaxy lived fast, burned bright and then burst into supernovas. Those explosions pushed gas and dust outward, sweeping the space clean and heating what remained. The shockwave shaped a cavity that our solar system now drifts through. The walls of this bubble still glow faintly in ultraviolet light, a reminder of energy released ages ago. Very thin gas fills the bubble. If you could scoop a handful of space here, you would find just a few atoms floating inside, far fewer than a breath of air. Yet they shape the edge of our solar system, pushing against the solar wind and forming borders that mark where our star's influence ends and the galaxy begins. Our neighborhood also holds other stars, though they are far apart by human standards. The nearest, Proxima Centauri, sits more than 4 light-years away. If we compare our neighborhood to homes in a countryside, each house sits miles from the next. We can only point telescopes, measure light, and dream of journeys that may one day cross the distance. Yet, even at that range, these stars shape our space. Their gravity reaches outward, their stellar winds spread through the void. Their light mixes with the faint background glow of the galaxy. Among our nearest neighbors are Alpha Centauri A and B, 2 stars locked in a slow dance with Proxima following behind like a quieter companion. There is Barnard's star, a fast-moving little sun that races across our sky faster than any other visible star, though still far away in distance. There is Wolf 359, a dim red dwarf that glows faintly like a dying coal in a dark furnace. Nearby, too, is Sirius, brightest in our night sky, shining like a lighthouse far across the cosmic sea. We often look up and see only points of light, but each point is a world of its own, with planets, winds, fields, and stories waiting to unfold. Dust also threads through the local bubble, tracing magnetic fields like fine threads in a cloth. We cannot see them with our eyes, but instruments reveal their presence, soft and faint, shaping how charged particles travel in the dark. The magnetic fields here are gentle but steady. They twist through empty space like invisible ropes, guiding the paths of cosmic rays and charged particles. They are part of the galaxy's larger field, stretched and bent by supernova blasts and the slow rotation of the Milky Way. Our heliosphere squeezes against them, making a shape like a teardrop as we move through the galaxy, with a rounded front where we face the flow of gas and a longer, softer tail stretching behind us. That tail reaches far, perhaps thousands of times farther than the space between the Sun and Pluto. And it trails through the neighborhood, like the wake of a ship cruising across still water. Every star around us has its own bubble too, its own protective wind and magnetic boundary. Some are large and strong, where young stars blow fierce streams of particles. Others are small and faint, barely pushing against the interstellar gas. If we could see these bubbles, space would look like a field of floating lanterns, each glowing sphere shaped by its star. Within the local interstellar neighborhood, we are riding through a faint cloud stretched across space. This cloud has a name, the local interstellar cloud. Some scientists call it the local fluff. But names aside, the idea is simple. The Sun, along with planets and all the small objects tied to it by gravity, is not moving through a perfect vacuum. We are passing through a region with gas and dust which shapes the outer border of our solar system. It touches the bubble of charged particles that the sun sends outward. Scientists discovered this cloud not by stumbling into it, but by reading the sky. They use starlight, like a flashlight held up in a dark attic, letting thin beams pass through the cosmic dust. Some stars appeared with tiny fingerprints in their light. These fingerprints, created by atoms absorbing certain colors of light, showed that gas sits between us and them. Over time, scientists mapped those clues and realized we were inside something. They traced the shape of the faint fog. They saw that our sun is not just cutting through open space, but moving inside a pocket of thin, warm gas. The local interstellar cloud is not huge on cosmic scales. It stretches around 30 light-years across. It is made mostly of hydrogen mixed with helium and trace bits of heavier elements. The temperature, though warm for space, would not feel warm to us. It sits at thousands of degrees, but with so few atoms, it cannot heat anything the way air heats your skin. In a sense, it is heat without touch, warmth without weight. The cloud itself shifts and flows, and our star sails through it like a ship gliding through thin fog. At some point, we may drift out of this cloud and into another region. The galaxy is full of similar patches, each with its own makeup and density. Each cloud shapes the solar system's outer layers in quiet ways. It is almost like weather, but on scales so large, we only see it by studying the sky and tracking signals from far-flung spacecraft. You could imagine the local interstellar cloud as a kind of frontier between stars. It is not a highway. It is more like a meadow between distant homes, each star with its own protective bubble and its own space to grow. In this thin environment, charged particles move. Magnetic fields stretch. Dust grains drift like tiny seeds carried by an endless breeze. Early astronomers noticed slight changes in starlight and wondered what lay between us and those distant suns. Later, as our tools grew sharper, those clues turned into maps. With the launch of satellites capable of sensing the wind from the sun and the particles beyond, we gained the ability to test what we saw in starlight against what spacecraft felt directly. It was not one breakthrough but many small steps. Voyager, in particular, became our scout. Long after it left planets behind, long after it stopped sending home photos, it carried instruments able to measure charged particles and the flow of energy. Its messages grew faint, yet they brought news from the edge of our world. They told us when the spacecraft crossed into a region touched more by interstellar space than by the solar wind. Those signals were not bright or dramatic. They were soft changes in particle counts, small clues gathered in silence, but they marked a moment in history. For the first time, a human-made object stepped into true interstellar space. The local interstellar cloud lacks the beauty of a glowing nebula or the drama of a star cluster, yet it holds a special kind of wonder. It reminds us that the galaxy is not a smooth void but a landscape, with hills and valleys made not of soil but of gas and dust spread thin. It reminds us that our journey through space is not just a straight line through nothing, but a passage through regions shaped by ancient events and distant stars. The solar system's future exit into the G-cloud. Far in the future, our path will carry us into a new region, which scientists call the G-cloud. It is another thin island of gas and dust spread across the galaxy, one more stop in the sun's long journey around the Milky Way. In tens of thousands of years, the solar system is expected to meet the border of the G-cloud. It will not be a clear line, like the edge of a country on a map. Instead, it will be a slow merging, a drifting from one faint ocean of atoms into another. At the human scale, nothing will seem different. The sun will still rise, the planets will still circle it, and night will still bring stars that look unchanged. But far beyond our sight, at the edges of the sun's protective bubble, the meeting will begin. The G-cloud is not fully known yet. It is still a puzzle we are trying to solve. We believe it might be warmer than the local interstellar cloud. We think it might contain more hydrogen. But like explorers guessing the shape of a distant island from a few scattered rocks, we hold more questions than answers. We know it is there. We know we are moving toward it. Beyond that, nature keeps its secrets, waiting for us to uncover them with time, patience, and technology. What we do understand is how the change could affect the solar system. When the heliosphere shrinks, more cosmic rays can enter. These are high-energy particles born in violent places far from here, in supernova blasts and spinning neutron stars. Today, the heliosphere blocks many of them. It acts like a great shield, catching storms from across the galaxy and breaking them apart before they reach the inner planets. But if the boundary tightens, fewer of those storms may be stopped. More could slip through, touching Earth's magnetic field and upper atmosphere. They might slightly increase radiation levels here. They could influence cloud formation or air chemistry in tiny ways. They might even change the background radiation that spacecraft and astronauts face. None of these effects would turn the world upside down. Yet they would be signs that even the calmest parts of space can shape life's home in quiet, indirect ways. In a sense, the G-cloud is another chapter in a journey that began before Earth formed. The Sun has already crossed other clouds in its 4.5 billion-year life. Every pass left tiny marks on its surroundings. Every crossing shaped the heliosphere in ways we would only learn to measure much later. When we speak of tens of thousands of years, the numbers feel unreal. They stretch so far past memory that the mind struggles to hold them. Still, we can imagine how our distant descendants might study that moment. Perhaps they will have instruments far beyond Voyager, spaced across the frontier like watchtowers along a coastline. Perhaps they will see the heliosphere tighten, see the density of interstellar atoms rise, see cosmic rays fall or rise as conditions change. They might treat this crossing as a natural event, recorded like the passing of seasons. Or if humanity has spread across space by then, they might treat it as a shared milestone, a quiet reminder that our home star keeps moving, no matter how settled we feel. Sometimes when people imagine the future, they picture rocket ships, strange planets, or distant civilizations. Yet part of our future is this slow drift through interstellar weather. The galaxy has shaped where we are and will shape where we go long after every footprint on Earth has faded. Mapping the nearest stars in 3 dimensions. When Earth circles the Sun, nearby stars shift slightly against the background of distant ones. This motion, called parallax, is like holding up a finger and seeing it move against a far wall as you blink one eye and then the other. It is simple in idea, but incredibly delicate in practice. Even the closest star moves only a tiny amount from our point of view. Yet those tiny motions allowed us to begin measuring distance, one star at a time, like surveying a town street by street. As tools improved, so did our maps. Telescopes grew sharper. Measurements became more exact. Soon, we could chart dozens, then hundreds, then thousands of stars in our region of space. These early maps were rough, like sketches made by lantern light. Still, they showed that our galaxy is not random. Stars gather, form groups, drift apart. Some travel through space like families staying close across centuries. Others wander alone, passing by like distant travelers on a quiet road. The picture that emerged was not flat, but layered and deep, with Earth sitting inside a web of motion and distance. Then came the space age, and with it, new eyes in the sky. In 1989, the Hipparcos satellite launched to measure star positions with precision far beyond what we could do from Earth. It charted the distances and motions of more than 100,000 stars, a leap forward like stepping from hand-drawn maps to satellite imagery. Suddenly, our understanding of the local stars became clearer. We learned the true distances to bright suns that sailors once steered by. We saw clusters in space that looked scattered in the sky. We began to trace streams of stars flowing through the galaxy like slow rivers of light. But the greatest leap arrived with the Gaia mission. Launched by the European Space Agency, Gaia carries a simple idea made powerful. Measure as many stars as possible with unmatched precision and build a 3D atlas of our section of the Milky Way. Gaia does not just watch a few stars, it watches more than 1 billion. Every day, it sweeps the sky, taking note of tiny changes in position, brightness, and motion. Over years, those changes stack up into the most detailed map humanity has ever made of the stars around us. With Gaia, astronomers see not just where stars are, but where they are going. They can trace paths across time, like drawing trails of fireflies in the dark. These paths show streams left by old star clusters that slowly stretched apart over millions of years. They show neighbors we never saw clearly before, faint stars hiding in darkness that now step forward into view. This new map changes how we think about our place in the galaxy. Before, space around us looked like emptiness with scattered bright points. Now it looks like a true neighborhood, with clusters of stars nearby, with quiet regions and busy ones, with pathways traced by motion. It is almost like seeing a city from above after only knowing it by walking its streets. Roads appear. Districts take shape. You understand why some areas feel quiet and others active. You see the whole structure at once. Astronomers use this map to answer questions once out of reach. They trace where stars near us came from and where they're going. Some seem to be passing through, visitors from other parts of the galaxy. Others belong to long-lived groups, siblings born from the same cloud billions of years ago. There are even stars that rush through the galaxy at high speed, perhaps flung by the gravity of the center, or pulled from other regions long ago. Gaia allows us to tell which is which. The map also helps us measure the shape of the local bubble. By tracking the light from nearby stars and how it dims or shifts, Gaia reveals places where dust grows thicker or thinner, marking the bubble's edges more clearly. Combined with radio telescopes and other tools, it helps us study the clouds inside the bubble, including the one we are drifting through. Without this map, our picture of the bubble would remain fuzzy. With it, we begin to see real structure, walls, gaps, and strands like the ribs of a giant shell carved by explosions long ago. Even planets beyond our solar system become easier to find when we know their stars so well. Gaia's precise measurements let astronomers detect tiny wobbles in star positions, revealing unseen planets tugging them gently. This will help us build not only a map of stars, but a map of nearby planetary systems, showing where there might be other warm worlds, other quiet suns like ours. With 3D maps, we no longer see the stars as frozen symbols. We see them as moving lights, as neighbors in motion, as fellow travelers in a vast and ancient system. What emerges from this mapping effort is not noise, but harmony. Space begins to look less like chaos. Every new measurement sharpens the picture, every year brings more detail, and somewhere far out there, our spacecraft move toward the edges, carrying tiny signals home, while Gaia watches from its quiet post in space, recording the stars with patience and precision. The more we map, the more the universe feels like a place with shape, with story, with structure. Alpha Centauri, a triple star in our cosmic backyard. There is a point in the sky where 3 suns live together, turning through space like dancers who know each other's steps by heart. They sit only a short cosmic walk from us, close enough that if our technology were just a little further along, we might send a ship there and wait for news in a human lifetime. This place is the Alpha Centauri system, our nearest star family beyond the Sun. It is nearby, yet unreachable for now, familiar, yet full of mystery. It stands like the first tree at the edge of a far forest. Alpha Centauri is not 1 star, but 3. 2 of them, Alpha Centauri A and Alpha Centauri B, orbit each other in a slow and careful loop. They are bright and warm, like the Sun, and close enough to each other to share a kind of cosmic companionship. The 3rd star, Proxima Centauri, is much smaller and darker, a faint red ember drifting farther out, loosely tied to the other 2. From a distance, these stars seem peaceful, like a small family living quietly in their corner of the galaxy. But space has no true peace. Gravity is always at work, guiding their paths as they circle, always moving, always falling toward each other, and then drifting away again. This system captures our imagination for many reasons. We wonder what might circle these stars. We know that Proxima Centauri has planets, with one, Proxima B, resting in the zone where liquid water could exist. It is a fragile hope. The planet may not be friendly to life. It faces powerful flares from its star, blasts of radiation that tear at atmospheres and scorch any gentle surface world that dares to form. Yet we keep watching, because possibility hangs there. A single piece of good luck in the physics of atmosphere or magnetic fields could mean a world with oceans and skies, and maybe life of its own. For Alpha Centauri A and B, the question remains open. With every new telescope and improved method, astronomers search for the slight tug or dimming that might reveal planets around them. So far, we have hints, but not proof. Even the uncertainty is thrilling, because a world around either A or B would be a wide and warm place, more like Earth's home than the tight rocky world around Proxima. It would give us a target filled with dreams. Standing in our mind's eye, inside that system, we can imagine a sky with two suns rising together or one following the other, painting strange shadows across alien soil. Plants there might spread in patterns shaped by their double sunlight, growing in ways we cannot picture. Nights might never be fully dark, only gently dim, with one small sun glowing like a lantern in the distance. And if any beings lived there, they would see our star as a faint point in their sky. A tiny reminder that another world turns far away. The pull toward this system is not only poetic, it is scientific. Alpha Centauri helps us test what we know. Studying nearby stars is a way to sharpen our tools and make sure our theories match reality. When we look at a star system so close, small differences matter. We notice the fine details of gravity between A and B. We model how planets might form around two stars instead of one. We measure flares from Proxima to understand how red dwarfs behave. This system becomes a kind of classroom, a place where nature lets us practice reading the rules of space. Entire generations have pointed telescopes toward this system and wondered what might be there. Science fiction has visited it again and again. Writers and dreamers treat it as the first door on the road to the stars, because it feels like a place we could reach if we try hard enough. Even early mission plans, like Breakthrough Starshot, have pointed toward Proxima and its tiny world. The idea is bold: to send small craft pushed by lasers, racing faster than any ship ever built. The journey would take decades. The craft would fly by fast, able only to glance, not stay. Yet even that small peak would feel like a victory against the distance between stars. If someone could stand far above the galaxy and watch us over millions of years, they would see the Sun and Alpha Centauri drifting near each other, not touching but traveling the same broad paths. They are not close friends, not bound, but familiar companions moving through the same ocean of stars. And we, tiny as we are, notice that. It feels strange that a star system 4 light-years away could feel like company, but in a universe so deep and wide, even distant neighbors feel dear. Someday, perhaps far in the future, humans or our distant children might see Alpha Centauri up close. They might step onto a world lit by twin suns. They might look back across space and see the sun as a faint spark, knowing home is behind them, but not lost, just farther than any horizon on Earth ever was. That thought holds a softness even inside the harsh truth of space. Alpha Centauri A and B, twin suns with Earth dreams. Alpha Centauri. A is about 10% more massive than our Sun. Alpha Centauri B is smaller, dimmer, but still steady, still gentle compared with the angry flickers of red dwarf stars like Proxima. These two together form a binary system that has held stable for billions of years. That matters. Life needs time. It needs quiet chances and long, calm stretches. Stars like these offer patience. Even so, this system is not simple. The two suns move in wide loops around their shared center. Sometimes they are far apart, leaving space where planets could hold steady orbits around each star alone. Sometimes they come closer, pulling on each other's gravity. A planet here would need to follow the right path. Too close to one star and tides might twist it. Too close to the middle, and the dance of gravity could shake its orbit until it becomes unstable. there is a narrow zone where a world could survive for ages. For years, there have been rumors of planets here. Today, many scientists believe at least one small world may circle Alpha Centauri B, tucked close in, but not so close that it would melt or freeze. It might be rocky. It might be roughly Earth-sized. We do not yet know if it breathes or spins or holds oceans that whisper under alien winds. But the chance alone makes this pair of stars feel like a frontier of hope. If such a world exists, it would live in the glow of a sun-like star. That alone is rare among planets we have found so far. Most known planets orbit small red dwarfs because red dwarfs are easier to study and more common. Alpha Centauri A and B offer steady warmth, long days, long nights, and calm skies that might allow oceans to stay liquid and air to stay thick. If Earth-like life can arise anywhere nearby, this is one of the most likely regions. And imagine a planet here with two suns in its sky. There might be mornings where one star rises, lighting soft golden plains, and then hours later, a second gentle dawn sweeps across, lifting the world's brightness just a little more. There might be evenings where one sun dips low while the other hangs like a stubborn lantern, stretching out twilight like a poetic pause. On some worlds, the two stars might appear close, on others far apart like two strangers who nod politely but rarely meet. The sky would shift in rhythms we have never seen, yet still feel peaceful, almost like Earth on its calmest days. Heat and light would shape the planet in complex ways. If both stars warmed the world at once during certain parts of their orbit, summers could grow rich and bright, feeding plants if plants exist there. When one star drifts farther away in orbit, seasons might cool, not sharply but with slow grace. A living world could adjust. Winds might carry warmth around its surface. Oceans, if present, could act as gentle memory banks for heat, holding summer in their depths and letting it out across winter months. This natural balance could offer stability, a key ingredient for life. Still, nature is not always kind. The binary orbit could tug on any planet's motion over long timescales. Small changes, small pulls, stacking over millions of years. Worlds here would need to be lucky or sturdy or both. A little tilt or shift might change weather patterns, sea levels, or the rhythm of climate cycles. Yet Earth has endured ice ages, asteroid strikes, and volcanic winters, and still carries forests, clouds, and birds. Life, once started, can be stubborn. That gives hope that a world in Alpha Centauri might hang on too. There is also a story here about worlds we may not yet see. Gas giants, rocky siblings, icy cousins in outer orbits. Maybe there are moon systems like tiny sculpted jewels, warmed by tidal pools and lit by double suns. Maybe there are asteroids filled with raw materials, drifting silently in the space between the stars. The Alpha Centauri system could hold a family of worlds. And if one of them has life, even simple life, it could spread from ocean vents to land, from shallow seas to sky. Time is patient. The universe grants billions of years, and life needs only a spark and a quiet place to grow its first whispers of breath. The enigma of Proxima B and its trustworthy doubts. Proxima B sits in a strange space between hope and doubt. When astronomers first announced it, the world buzzed with excitement. A planet in the habitable zone of the closest star to our Sun, a place where liquid water might exist. Headlines called it Earth-like, and for a moment it felt as if another cradle of life might be only 4 light years away, waiting for us to knock on its door. But nature rarely hands out answers so easily, and Proxima B is a reminder that excitement and truth do not always walk side by side. It is a planet wrapped in mystery. Not everything we hope about it can be trusted. Some of the information comes from hints so faint that scientists debate what they really mean. Some data sits right on the edge of what we can measure. To understand why we are both thrilled and cautious, it helps to know how Proxima B was found. Astronomers did not see it directly. Instead, they watched Proxima Centauri wobble. That tug told us a planet was there. It told us the world had roughly the mass of Earth. It told us it orbited close enough to the star to maybe hold warmth. But maybe is a big word in science. The wobble method, called radial velocity, can give only part of the story. It tells us the minimum mass, not the true mass. The planet could be a rocky world like Earth, but it could also be heavier, thicker, more like a mini Neptune wrapped in gas. We do not know its size, we do not know its surface, we do not know its air, if it has one at all. The word Earth-like can mean many things, and in this case it mostly means Earth-sized. That alone is not enough to make a place friendly to life. The star it orbits adds to the puzzle. Proxima Centauri is a red dwarf, a small and dim star, glowing more like a warm coal than a bright flame. Its light is soft and reddish, and its heat fades quickly with distance. To stay warm, Proxima B must sit close, far closer than Earth sits to the Sun. It takes only about 11 days for the planet to circle its star. If someone could stand on its surface, the star would hang huge in the sky. But closeness to such a star brings danger. Red dwarfs are known for their fierce tempers. Proxima Centauri has been seen to flash with powerful eruptions that could strip a planet's atmosphere like wind blowing dust from a stone. A planet might begin with oceans and air, only to lose them under the steady hammer of radiation. That does not mean Proxima B is dead or hopeless, but it sets a challenge. Life there, if it exists at all, would have to endure conditions harsher than anything Earth has faced. Some researchers picture Proxima B with a strong magnetic field, guarding it like a shield. Others imagine thick clouds or oceans protecting life below. Some say it could be tidally locked, with one side always facing its star, one side always night, and a band of twilight in between where temperatures are just right. These are interesting ideas, shaped by models and theory, but they are not proven. Even the planet's existence itself has been questioned once or twice. When signals are tiny and stars are noisy, false positives can happen. Tools drift, data shifts, stars can mimic planetary tugs through magnetic changes or surface activity. Most astronomers agree Proxima B is real, but they still check and recheck, like someone making sure a bridge is strong before crossing it. That caution is not doubt in progress, it is respect for the truth. Telescopes on the ground and in space are being built to look for thin signals in starlight, a slight change in color or brightness that might reveal what the planet's surface reflects or what gases fill its sky. If we detect oxygen or methane or strange patterns that do not match simple chemistry, the excitement will rise again. If we detect a dry, airless rock, the dream will shift elsewhere. Either result would teach us something real about worlds near red dwarfs, and science grows from learning, not only from hoping. For now, we stand in a curious middle ground. Proxima B feels close enough to touch, yet remains hidden behind the limits of our tools. This uncertainty reminds us that the universe does not bend to our wishes. It teaches us to love the hunt for answers as much as the answers themselves. It keeps us humble. When we hear the phrase Earth-like, we learn to ask questions instead of breathing easy. How Earth-like? In what way? And for how long? The cosmos is full of worlds that sound promising but hide truths far stranger than simple labels can hold. And yet, even with doubts, Proxima B pulls at us. If one day we build ships that travel between stars, this world will almost certainly be among the first places we visit. We may find nothing but rock and silence. Or we may find clues, even the smallest ones, that life can rise under alien skies, in places where logic once said it should fail. That possibility is worth all the patience and caution science demands. The strange light of Proxima's flares. The light from Proxima Centauri does not behave like the steady glow we know from our sun. Instead, it flickers and lashes out, as if the star breathes fire in sudden bursts. Most nights in that system would be calm, red light washing over any nearby world in a constant soft hue. But then, without warning, the star would erupt. It would brighten in a flash, shooting energy across space, enough to turn a peaceful alien sky into a violent storm of light and radiation. This behavior is the nature of many small stars. Proxima Centauri is what astronomers call a flare star. Because it is small, it stirs itself more wildly inside. Magnetic fields twist like coiled ropes, storing power until they snap. When they snap, the star sends out a wave of particles and light thousands of times stronger than anything Earth experiences from the Sun in a normal day. Sometimes these flares are so intense that Proxima briefly becomes brighter than usual. On Earth, our atmosphere and magnetic field protect us from most solar flares. They block harmful radiation and keep our oceans calm. Life here grew under that natural shield. But for a planet close to Proxima, the danger is sharper. With the star so near, each flare can strike harder. If the planet lacks a strong magnetic field, the radiation could slip into the atmosphere, break apart molecules, and strip the air away over long stretches of time. Even a strong shield might struggle under repeated storms. To life on such a world, if it exists, light might not always be a gentle gift. Perhaps any living thing there would hide beneath soil or water, shielded in caves or under thick layers of rock. Perhaps life would sleep when the star bursts, waking only in quiet hours. Maybe cells would learn to repair themselves from radiation, the way desert plants survive heat, or deep-sea creatures survive pressures that crush metal. Nature can be clever when pushed, but it must first survive long enough to learn. Some flares last minutes, others hours. One flare observed in recent years was so strong it surprised researchers. Light leapt across a wide band of energy, including ultraviolet and X-ray waves, the kind that can tear molecules apart. For a moment, Proxima shined hundreds of times brighter in some wavelengths. Then, just as quickly, it dimmed again, sliding back into its normal calm glow like nothing happened. This rhythm of quiet and outburst is not chaos. It is a kind of pattern, tied to the star's age and size. Young stars often flare more, older ones calm with time. Proxima sits in a middle place, old enough to have slowed a little, young enough that it still snaps with energy. It rotates slowly now, which means it has lost some of its early fury, but its heart still churns with magnetic storms. We do not see these flares with our eyes in the night sky. Proxima is too faint. Instead, we detect them with telescopes tuned to different colors of light, eyes made of mirrors and sensors that catch what human sight cannot. When a flare hits, instruments record a sudden spike, a quick leap in brightness. Computers track the change, then the slow fall back to normal glow. These flares also tell us something about the life cycle of stars. Our Sun flares too, but far more gently. It has quiet years and more active years. These cycles come from its magnetic field turning like gears inside. Proxima's gears spin differently. Because it is smaller, heat flows through it in another way. The whole star churns top to bottom like boiling water, mixing constantly. That motion stirs magnetic fields into tight, twisted shapes. When those shapes snap, the star lights up. Understanding these flares helps us understand how stars stay alive, lose energy, and grow older. And while we think of stars as steady, they are not always peaceful homes for planets. The habitability of a world is not just about distance from its star or the presence of water. It is also about whether the star allows quiet enough time for life to find its footing. A world bathed in violent radiation might have seas, might have rock, might even have chemistry ready to spark life. But each flare would test any new organism, tearing fragile beginnings apart before they can settle. It does not make life impossible, it simply raises the stakes. Nature must adapt or it waits somewhere else for a calmer light. What tidal-locked worlds might really be like? It is strange to imagine a world where the sky never changes. A place where sunrise and sunset never happen because the world never turns. One side drinks endless daylight, soaked in heat and blinding sky. The other lives under a forever night, wrapped in freezing cold and stars that never move. These are tidal-locked worlds, planets so close to their stars that gravity grips them like a firm hand and refuses to let them spin freely. For a long time, many imagined such worlds as lifeless, a scorched face cooked by never-ending light and a frozen face turned to stone. But as we learn more, we start to see that the line between hopeless and hopeful is not so simple. Nature, as always, has hidden ways. Even a locked world breathes. Its air moves. It has winds and storms that carry heat like invisible rivers. On the bright side, warm air rises, then flows toward the night. On the dark side, cold air sinks and travels toward the day. This turning of the sky, the slow swapping of heat and cold, can smooth out what looks like a harsh divide. It may not make the world gentle, but it can make it possible. Picture that line between the day side and the night side, a soft ring stretching around the planet like the edge of a coin, not too hot, not too cold, a land that lives in everlasting twilight. Here, the star would hang low on the horizon and never move. The light would always look like early morning or late afternoon, painting the land in shades of gold and soft blue. Plants, if they exist, might reach toward that steady glow. Water, if it settles, might pool in rivers and lakes that never freeze and never boil. This twilight ring is the hope that life does not need a spinning Earth-type world. It might only need balance. Not perfect balance, just enough balance to build shelter against extremes. Some models show this ring could be wide like continents. Others picture it narrow, a thin band where survival is a tight fit. But even thin hope is still hope. The air itself could play hero or villain. If the world has thick air, like a strong blanket, heat can travel better. It can keep the dark side from becoming deadly and stop the bright side from burning out of control. If the air is thin like Mars, then nature is harsher. Heat stays trapped on one side, cold rules the other, and life becomes a hard gamble. Clouds might also join the fight. They could form above the bright side, acting like a giant sunshield. They would reflect light and cool the surface. The more clouds, the more even the planet becomes. Clouds are not just weather here. They are armor against endless day. Water adds another twist. If ocean covers the planet, it could move heat far better than air. Warm currents sliding into the dark, cold currents returning to the light. Even if the surface freezes on the night side, a deeper ocean might still flow, kept warm from below by a restless core. Of course, a world like this still carries risks. Weather may be wild, like storms that never end and winds that shake mountains. The border of night and day might shift if air patterns change, turning safe land into danger over centuries. And if the star flares often, then no matter how perfect the balance, the sky itself becomes the threat. On Earth, time is marked by days. It shapes sleep, seasons, farming, migration, culture. But on a locked world, time might feel different. A person there would never see sunrise or sunset. Time might be counted by tides or air cycles or blooming seasons. Their sky would tell a story, but not one we know. People would learn to live by slow change, not daily rhythm. Even the idea of direction shifts. On Earth, north and south feel natural. On a locked world, toward the star and away from the star might become the true compass. The side facing the star is home to heat, light, growth. The side turned away feels like danger, mystery, maybe courage. Imagine traveling toward the dark. With every step, starlight fades and the world turns colder. It would feel like walking into myth. If beings grew on such a world, their bodies might show their sky. Eyes tuned to dim light, skin tough to heat or cold. Perhaps two very different cultures could form, one near the warm middle, the other pushing into colder land. Night folk might adapt to shadow and silence, while day folk thrive in bright air and gentle gold light. And if they ever looked up and saw another world turn like ours does, they might find it strange. A spinning planet might seem unstable to them, like a dizzy traveler who cannot stand still. They would not understand why someone would want sunrise at all. We are used to thinking of Earth as the model. Our colors, our wind, our sky shape our sense of what life should look like. But in this new age of worlds around other suns, we learn again and again that our shape is only one idea the universe tried. Tidal locked worlds are not mistakes. They are simply different. They trade days and nights for a slow, steady rhythm. As telescopes sharpen and we find planets where the star sits still in the sky, we must hold on to wonder. We once believed desert dunes could not grow trees. Then we found oases. We believed deep caves were empty. Then we found glowing bacteria. Life has a habit of crawling into corners and lighting them up. So, when we look at these worlds forever turned toward their suns, it is tempting to whisper that they are broken, but they are not. They are locked in a quiet struggle between fire and ice, and that struggle might be the very thing that shapes life. It is possible that somewhere out there, a world in eternal sunset has oceans that breathe steam and slow rivers that never freeze. It is possible that wind travels like a heartbeat, steady and sure, feeding valleys where strange forests stretch toward a sun that never moves. It is possible that minds look up at their dim sky and wonder if somewhere beyond the stars there are planets that spin, bringing light and dark day after day like a strange miracle. We cannot yet know, but when we dream of worlds beyond our own, we should not picture only Earth clones. We should picture twilight. We should picture heat meeting cold at the edge of forever night. We should picture life finding a way on a world that never turns. Stars on close approaches. Long ago, a faint red dwarf named Schultz's star passed by our solar system. It came within about a light year, brushing the edge of the Oort cloud, where icy objects sleep in the dark. If our entire history as a species were a single night, its visit would have come and gone like a soft wind outside. We did not see it. Not our ancestors, not their ancestors. Only modern astronomers uncovered its path by tracking its speed and direction backward through time, using math like a lantern in a cave. Its visit may have stirred a few comets in their icy beds, the way a passing truck rattles loose stones on the roadside. A few may have begun slow journeys inward, taking millions of years to reach the inner planets. In the far future, another star will come. Gliese 710, a small orange star, is drifting toward us right now. In about 1.3 million years, it will pass a little closer than Schultz's star did, close enough to slide through the outer edge of our comet cloud like a hand brushing tall grass. It will not tear worlds apart or break planets loose. That kind of danger belongs to rare wild events. But Gliese 710 may scatter comets like grain thrown in a field. Centuries after its passing, long icy travelers might wake and begin slow drops toward our inner worlds. To future humans or whatever beings stand where we stand, these comets might look like whispers from deep time. They will not know the star's name by sight, but math and records will tell them where the disturbance came from. They might look at their sky and feel a little more aware that space is not empty, but full of travelers and tides. There have been other close stars across history, and there will be more. Barnard's star came near in the past and now moves away with its quick step. Captain's star, once part of a shredded ancient galaxy, crossed our neighborhood on its long journey around the core. In another 5 million years, the massive bright star Gamma Microscopii will glide past at a respectful but noticeable distance. The solar system feels each touch, even if we do not. Astronomers track these motions with growing skill. Missions like Gaia do not just map where stars are, they map where they have been and where they will go. Imagine a future where beings on Earth watch Gliese 710 draw closer. They will see it slowly brighten in their night sky, turning from a faint point to a noticeable glow over tens of thousands of years. It will not rival our sun or even our moon, but it will join the sky as a new visitor, steady and patient. In that time, they might feel a quiet thrill, a neighboring star, not too far, not too close, just near enough to remind them that the galaxy is alive. When it leaves again, the sky will return to its older shape, but not quite the same. Some comets will have been lifted from slumber. Some long arcs through space will have begun. And deep in the records of those future astronomers, the passing will be marked as one more thread in the long braid of stellar encounters. And somewhere out there, perhaps near Gliese 710 or another drifting neighbor, another planet may watch us in return, waiting for us to pass by their edges in a time so slow it feels like forever to a human heart. Stars that will pass closest in the far future. Beyond Gliese 710, other stars are charted on the galactic road ahead. Most of them will never get as close. Many will pass at safe distances where the only change they bring is a slow shift in the map of stars in the night. Some will approach within a few light years, close enough to belong to the same short chapter of our galactic neighborhood. As the next few million years unfold, the nearby sky will change stars as slowly as seasons change on Earth. One star called HIP 85605 was once thought to be a major future visitor, perhaps passing within a light year or less. But better data changed that picture, pushing it farther away and reminding us how much of cosmic forecasting depends on precise numbers. A small shift in measurement today can change the story of a million years from now. Even so, the list of likely future close stars continues to grow sharper with time. Gaia and other missions feed us clearer maps, so our predictions no longer feel like vague guesses, but careful projections grounded in measurement. Gamma Microscopiae is a larger star than Gliese 710, bright and strong, the kind that lives a shorter, more intense life. By the time it arrives near us, Earth's continents might form a new supercontinent. The beings living through that era may have no trace of us, or may carry our stories in strange future languages. They will look up and see a sky reshaped by time, where bright newcomers appear where today we see only faint points. Some stars, like Ross 248, are moving toward us now and will one day come closer than they stand today. They will join the list of our nearer neighbors before drifting away again. The galaxy feels like a slowly shifting crowd, where nothing stays in one place forever. Over tens of thousands of years, constellations we know today will stretch and twist like clay warmed by the hands. Patterns like Orion and Cassiopeia will bend until they are unrecognizable. A human today would not recognize the sky of a million years from now. Only the Milky Way's broad band across the heavens would remain familiar, a river of stars that outlives generations and species. Even in this future, though, the quiet nature of these encounters remains. None of these passing stars are expected to break our solar system apart, or steal planets, or plunge into chaos. The distances sound close on cosmic scales, but they are still so vast that stars do not collide and planets do not smash. Instead, the story is one of slow drifting, gentle tugging, and background change. For beings far in the future studying these same paths, Gliese 710 or Gamma Microscopiae may be as familiar as our moon is to us. They may carve maps of the sky with such detail that future flybys become as predictable as seasons in ancient calendars. As we push forward in imagination, we see a timeline stretching far beyond human memory. 5 million years, 10 million years, 50 million years. In that time, whole families of stars will cross paths at distances that feel close in the scale of the galaxy, yet remain safe. Our Sun will keep circling the Milky Way, completing its long orbit every 230 million years or so. Each lap brings it through changing neighborhoods, star clusters, wisps of gas, ancient remnants of long-dead suns. So the future sky will not be ours, but it will still be a sky full of stories. It will hold new bright visitors, slow and silent, passing without hurry. They will not bring fire or ruin. They will bring a soft tug at the far edge of our space and then continue onward. In the long glow of the galaxy, stars drift like lanterns on a slow current. Our Sun is just one among them, moving through time and space, passing neighbors now and neighbors yet to come. The silent red wanderer, Barnard's star. There is a lonely traveler moving through the darkness near us, a star that slips across the sky faster than any other visible from Earth. Not fast in the way a shooting star is fast, flashing and burning out in seconds, but steady like a silent runner crossing a field while everyone else stands almost still. This star is Barnard's star, a small red dwarf not far from the Alpha Centauri system. Barnard's star is about 6 light-years away, making it one of our nearest neighbors. Over decades, it shifts its place against the background of more distant stars. Astronomers call this motion proper motion, the slow drift of stars as they travel around the galaxy. Barnard's star holds the record for the fastest proper motion of any known star near us. We are moving too, carried by the galaxy's structure. But Barnard's star moves differently, at a sharper angle, like someone walking through a crowd headed somewhere else. It may not be dramatic to the naked eye, but over generations, the shift becomes clear in the precise measurements of telescopes. In old star charts, Barnard's star sits in one place. In new ones, it has marched onward. Barnard's star is old, far older than our Sun. Many estimates place its age at about twice the Sun's age or even more. It has lived through cosmic ages we can barely imagine. When our planet was still forming, when Earth was a bubbling, molten place with steaming seas of early chemicals, Barnard's star had already been shining for billions of years. It has seen stars born and die around it, and it will likely outlast our Sun too. Red dwarfs burn slow. They are like candles with tiny flames that last for trillions of years, deep into futures where our own Sun will be only dust and memory. But the star's soft light hides a restless spirit. In the past, there were claims of planets orbiting it. Some early observations suggested 2 worlds might circle Barnard's star, hinting at a system waiting to be explored. For decades, these claims stirred excitement. More recent searches have been careful, using better data and finer tools. One possible candidate planet appeared in studies, believed to be a cold super-Earth circling at a distance. Yet as scientists dug deeper, the signal faded into doubt. It may have been noise, a ghost in the data. Right now, we cannot say there are planets here, not with confidence. If there are worlds, they are likely small, icy, and hard to find. Yet this mystery does not weaken the star's importance. A nearby star with such clean space around it becomes a kind of baseline, a reference point. It helps us understand what an old red dwarf looks like when not surrounded by strong companions. It teaches us how these stars move, spin, and age. In studying Barnard's star, we study the quiet middle chapters of a star's life. Barnard's star also reminds us how dynamic our region of the galaxy is. Stars drift, wander, and sometimes come close enough to disturb each other's outer regions. Long ago, Barnard's star was farther away. Long into the future, it will move past us and continue on its way. Each star around us has its own path, each shaped by gravity from the galaxy's heart and the pull of neighbors long gone or still unseen. When we watch Barnard's star, we are, in a sense, reading a travel journal of our corner of space. Its speed hints at past encounters or long journeys from different parts of the galaxy. It may have brushed near other star systems in ancient times, altering comet clouds or drifting past young worlds still forming. Now, it passes through quieter space, close enough for our curiosity to reach it, but far enough that we can only study from a distance. If it did have planets, what would they be like? Around a star so small and faint, a world would need to huddle very close to stay warm. Days might be dim, more like endless red sunset than bright noon. Plants, if they evolved, might drink in every scrap of light and perhaps reflect dark colors, not green. Life would have to adapt to a quiet trickle of energy, maybe rising slowly over ages, built for patience, not speed. Understanding these lonely stars gives us context when we look at brighter or more dramatic systems. It helps us map where life might thrive and where space might feel empty, at least as far as biology goes. The galaxy is not one story, it is thousands of stories. How Barnard's star fooled astronomers for a century. Stars do not scheme. But by its steady, quiet motion and the limits of our early tools, Barnard's star led astronomers down a path full of hope, confusion, and careful lessons. The story began in the early 20th century, a time when telescopes were improving and hopes for finding planets beyond our solar system were just beginning to take shape. Back then, the idea of other worlds was not a proven fact. It was a dream hanging in the air, waiting for evidence. Many astronomers believed that if our sun had planets, surely other stars must have them too. But belief was not enough. They needed data, and Barnard's star, with its fast motion and closeness to Earth, became a tempting target. In the 1960s, a well-respected astronomer named Peter van der Kamp announced that Barnard's star had at least 2 planets. If true, this would have been the first confirmed planetary system around another star. The news echoed through science circles and magazine headlines. a calm, faint red dwarf suddenly became a cosmic celebrity. But the problem was not the star, it was the telescope. Van der Kamp worked with a small refracting telescope at Swarthmore College. He made careful measurements over years, tracking slight shifts in the star's position. These changes looked meaningful. They seemed to match what planets would do, tug a star as they orbit it, producing a tiny wobble. Yet the wobble did not come from planets. It came from adjustments to the telescope itself. Each time the lens was cleaned or repaired, or the mount was adjusted, the behavior changed just enough to mimic a signal. The machinery, not Barnard's star, created the illusion. Later, astronomers examined the data and the history of the telescope's maintenance. They showed that the star did not actually wobble the way Van der Kamp thought. The signal vanished when more accurate tools were used. What many had believed for decades began to fade like mist in sunlight. Barnard's star did not have those planets after all. There was no dishonesty. It was simply the slow correction of science as better measurements replaced older ones. But the lesson was sharp. It showed how eager minds, staring into the dark, can sometimes see patterns where none exist. It showed how tiny errors can grow into big claims when data is fragile and tools are stretched to their limit. Even after Van der Kamp's claims faded, the star was not finished playing with our expectations. Modern instruments, far more precise than anything in the 1960s, began to search again. If planets existed here, they would reveal themselves in starlight, in radial shifts, or in subtle patterns across long stretches of time. For a moment, it seemed like a new signal emerged, this time suggesting a single cold super-Earth. The finding made headlines. It was gentler than the earlier claims, backed by more careful analysis, but still uncertain. Then, as more data poured in, the signal began to weaken. It might be a planet, or it might be another trick of noise and timing. Each time astronomers thought they grasped the truth about Barnard's star, it shifted slightly out of reach. When you are looking for very small changes across very big distances, reality can blur. Today, we know planets are common. We have found thousands. But back then, Barnard's star carried that dream alone for many people. It was a placeholder for hope, even if the planets turned out to be illusions. In classrooms and observatories, students still study the story. They learn how Van der Kamp worked, how he cared for each measurement, how he believed in what he found. They also learn why those findings did not last. His mistake pushed others to invent better methods. It inspired new instruments, better thinking, more careful checks. In a way, Barnard's star did give us something big. It gave us progress. When astronomers look at it today, they do so with tools that once seemed like dreams, precise instruments in space, surveys scanning millions of stars, computers that see patterns humans cannot. They see Barnard's star not as a trickster, but as a teacher. In quiet observatories, as digital screens trace tiny changes in starlight, and researchers watch data rise and fall like small waves, Barnard's star keeps moving steadily. Every now and then, a scientist will look up from the numbers and imagine those early years, those first claims, those decades of hope and correction. They might smile at the thought that this simple nearby star once carried so many dreams on its small shoulders. Barnard's star fooled us, yes, but in doing so, it helped shape the way we look for life and planets today. It made the field humbler, sharper, and more careful. Gliese 65. The flare twin system. Not far from where Barnard's star drifts, another pair of small suns dances together in a tight orbit. They are called Gliese 65, also known as BL Ceti and UV Ceti. These two red dwarfs form a binary system, circling each other like partners who never stray far from each other's light. They do not shine brightly, and you would never see them with your naked eye from Earth. Yet they pulse with an energy that feels restless, alive, and sometimes dangerous. If stars had moods, these two would live on the edge of sudden excitement, flaring without warning. Gliese 65 sits just over 8 light-years from us. Like Proxima Centauri, these stars are small, cool, and dim. If you stood near them, the sky would stay the color of late evening even at noon. Their light carries more heat than brightness, and their surfaces hide churning storms and magnetic tangles. The two stars orbit each other every few decades, locked in a slow cosmic waltz. Their pull keeps them bound, each tugging the other in a steady rhythm. But while their orbit is smooth, their surfaces are not. They sometimes scream into space with sudden bursts of energy. Astronomers have watched them flash so brightly for moments that they briefly outshine their usual selves many times over. Among the pair, Ceti is famous. It gave its name to an entire class of flare stars. In one moment, Ceti may appear peaceful. In the next, its magnetic fields twist and break, unleashing storms across its surface. If you could somehow live near such a star, you would see sudden flashes in the sky, as if the sun above you was having lightning storms across its surface. It would not be a gentle place. It would be a landscape of constant surprise. The sun is calm most of the time. Proxima flares often, but even Proxima has days of quiet. Gliese 65 is like a more intense cousin, showing us the extreme end of stellar weather. It forces scientists to consider whether life needs calm skies or simply needs time and clever strategies. Maybe life in such a place evolves slowly, learning to adapt over billions of years. After all, these stars live far longer than stars like our Sun. If life can survive the early storms, perhaps it has eons to flourish later. Imagining a planetary system here feels like imagining a small town built next to an active volcano. It might seem risky, but not impossible. And if such worlds exist, they could hold secrets about survival in hard environments. Life is stubborn. The universe might be too. Astronomers watch Gliese 65 to learn how flare activity shapes its surroundings. They measure light curves, the brightening and fading recorded by telescopes. They track radio bursts, signs of magnetic storms crackling across the star's surfaces. They study how long flares last, how often they happen, and how intense they can be. Each eruption becomes a clue about the behavior of red dwarfs across the galaxy. Since red dwarfs make up most of the stars in the Milky Way, understanding a place like Gliese 65 is a key part of understanding our galaxy's habitability. What makes this pair even more interesting is that their behavior is not random. There are patterns, rhythms, cycles. Sometimes they flare often. Sometimes they quiet down. It is like watching weather seasons not on Earth, but on stars. The more we observe, the more we see hints of rules guiding these eruptions. Not chaos, but rough order. The fires rise and fall, driven by rotation, magnetic fields, and deep layers of plasma churning slowly beneath the surface. Proxima is a single star. Its flares sometimes feel like sudden snaps in a lonely sky. Gliese 65 is a duet. The two stars may influence each other's magnetic fields as they orbit. They may stir each other's activity. They feel like winds feeding a shared fire, not always in sync, but sometimes echoing each other's energy. Studying one helps us understand the other. In older astronomy books, stars like these were simply points of light with strange behavior. Today we see them as characters in a cosmic story, restless, ancient, and pulsing with silent storms. They are reminders that our quiet sun is not the rule. It is a gift. If Earth had formed near a star like Gliese 65, our story might have been very different. Maybe slower, maybe stranger, maybe never written at all. Tau Ceti and the search for quiet suns. If stars had personalities, Tau Ceti would be the patient one sitting at the back of the room, watching everything with care, speaking only when needed. The star is about 12 light-years away, still close on a cosmic map, but far enough that its light feels like a whisper instead of a neighbor's shout. It is smaller and slightly cooler than our Sun, yet not so different that we would call it alien. What makes a star quiet in the language of science? It does not burst out with intense flashes. It does not throw storms of radiation as often as young and restless stars do. It turns its plasma oceans in a stable way, not in violent churns that break magnetic fields into wild fury. In other words, Tau Ceti keeps its temper. A peaceful star can be like a gentle parent to planets. It lets atmospheres stay thick instead of stripping them away. It gives oceans time to form instead of boiling them off. It allows fragile molecules to link into chains, to try shapes, to fail and try again. It gives chance a long runway. That is what life seems to need. Time and steady conditions, not constant chaos. Tau Ceti also holds something even more precious to researchers: dust. But not dust like under a couch or floating in sunlight through a window. This is cosmic dust, leftovers from the star system's early days, small pieces of rock and ice drifting in wide belts. Astronomers see it through infrared eyes, sensing heat instead of light. The dust tells us stories, hinting that building blocks for planets once floated thick here, maybe still do. But dust also warns us. Too much debris could mean constant asteroid strikes, like living in a neighborhood where rocks fall from the sky now and then. Calm star, busy backyard. That kind of mix brings mystery. We have found hints of planets here. Signals rise and fall in Tau Ceti's motion, as if invisible worlds tug at it. Nothing is confirmed yet in a perfect way, but the evidence draws excitement. Some possible planets would live near the habitable zone, where temperatures might allow liquid water. We do not know if they are rocky like Earth, or thick with gas, like mini Neptunes. We do not know if they have atmospheres or bare rock faces burned by time. But even the chance is enough to make telescopes breathe deeper. For now, Tau Ceti remains a picture framed by questions. Stars change as they age. Even calm ones have cycles. Our Sun has 11-year rhythms of activity, rising and falling like tides. Tau Ceti has its own patterns, softer and slower, but real. 100 million years from now, it might flare more, or it might grow even calmer. We are watching only a moment in its long life. There is also the idea that a quiet star might not stir planets enough. Some scientists wonder if small bursts of energy are needed to spark early chemistry. Lightning in atmospheres, solar winds nudging molecules, ultraviolet rays breaking apart and rebuilding compounds. Too calm and life might have trouble lighting its first match. But we do not know. Earth is one example, not the rule for all worlds. Looking at Tau Ceti is like looking into a second mirror of our own solar story, but with slight differences, like a dream version. Its planets, if they exist as we expect, could be thicker with rock or drier or younger in their geological moods. We imagine steady skies, soft star glow, no sudden flashes ripping across air and sea. We imagine a world where trees could stretch without fear of sudden radiation storms, where oceans might not hide life deep to escape ultraviolet punishment. Yet imagination always walks beside caution. Many calm stars are old stars. Time is kind, but it also slowly steals heat. If Tau Ceti is farther along in its life than our Sun, its planets may have formed early, and perhaps dried out or grown cold before life had a chance. Long, slow clocks can still run out. The quiet cradle could turn into a quiet tomb. Astronomers listen to Tau Ceti for more than planet clues. They also listen for signals. For decades, this star has been a common target in the search for intelligent life. Something about its sun-like nature makes it feel like a possible home for minds, if minds grew there. Radio dishes have watched it, waiting for unnatural patterns in the static, waiting for the universe to speak. So far, Tau Ceti keeps its silence. When we study Tau Ceti, we are not just studying a star, we are studying a type of hope. The hope that somewhere nearby, nature made a second try at building a peaceful cradle like ours. The hope that life does not need to cling to stormy red suns or strange blue giants, but can settle under a golden light, not too different from the one that feeds leaves on Earth. The quiet stars do not call attention to themselves, but sometimes the softest voice in a room carries the most promise. Tau Ceti sits there in the night, patient and steady, waiting for our telescopes to grow sharper, our methods to improve and our curiosity to deepen. Sirius, the blue-white beacon, next door. Sirius has a sharpness to it, a bright bite in the night sky that feels almost personal. Sirius shines like a young athlete in a crowd of elders. Its light arrives with a kind of impatience, cutting through winter skies as if eager to remind us that stars are not all quiet and slow. Some of them burn like they have something to prove. This brightness fooled ancient viewers who thought it might bring heat just by appearing. It rises in the sky, and in many old cultures, it marked the start of hot seasons. People feared it, respected it, watched it. Now we know the truth. Sirius is bright not because it is close alone, but because it is both near and powerful. Light races from its surface as if pushed, not just released. It is a blue-white star, hotter than our sun. Younger too, burning through its fuel faster, like someone sprinting through life instead of walking. Youth in stars shows itself not in smooth skin or quick steps, but in heat and hunger. Sirius is still in its stable phase, but it runs faster through the cosmic clock than our sun does. While our star stretches out its life like a long, slow story, Sirius feels like a short novel written in bold strokes. It is about 240 million years old, hardly out of its early chapters. Yet it will not last as long as the sun. It will burn bright, then fade. A flash compared to the long, steady glow of stars built for endurance. When we speak about Sirius, we do not speak about one star alone. It has company. A white dwarf, Sirius B, circles it like a pale ghost. At first glance, this companion seems weak, almost lost in the glare of the main star. But that small white glow has stories of its own. Once, Sirius B was larger, grander, a star that lived fast and ended in collapse, leaving behind a dense core. Now it sits beside Sirius A, almost like a memory turned into matter, a reminder that even bright stars eventually fall inward under their own weight. This pairing gives the Sirius system a layered feeling. On one side, you have youth and power, heat and speed. On the other, quiet density, packed history, the calm of a star that has already lived through its bright days. One star races forward, the other stands as proof of what will come. In space, time is often visible if you know where to look. Sirius makes that clear without needing words. The orbit between these two stars stretches over about half a millennium. They dance slowly, their pull on each other locked and steady, a gravity handshake that will last far longer than human history has so far. Astronomers once puzzled over that motion. They thought something invisible might be tugging at Sirius, maybe planets or another hidden star. For a while there were whispers of a mysterious third companion, but as instruments improved, those ideas faded. Sometimes the universe tricks us with small wobbles, it hides secrets in noise, and we chase them like fishermen seeing ripples on water, unsure if it is a real catch or just wind. Sirius is not a star where we imagine friendly worlds with soft skies and calm oceans. Its light would be too fierce, its warmth too sharp, its lifespan too brief for life to settle comfortably. Planets around such a star would face storms of radiation and strong stellar winds. Even if a world could form in a stable orbit, time would not be on its side. Sirius offers brilliance but not patience. Yet that does not make Sirius less important to us. It shows a type of star common in the galaxy's early youth, when bright blue suns lit up the newborn Milky Way like stadium lights. It reminds us of phases our own sun never went through, phases of raw energy and quick burning. Sirius lets us see what speed looks like when it comes to stellar life cycles. Looking at Sirius through a telescope, the light wavers in our atmosphere like water rippling over a silver coin. It feels alive, restless. Many young stars do this, but Sirius does it with flair. If Proxima is a cracked ember and Tau Ceti is a steady candle, Sirius is a blowtorch. There is beauty in each, but you would not warm your home with a blowtorch. Astronomers use Sirius as a kind of lighthouse. Its brightness helps calibrate instruments. It serves as a reference point in the sky, a landmark in the great dome overhead. When telescopes shift and measure, they often steady themselves by checking Sirius, the way sailors in the past held their course by familiar stars. Even in modern science, old sky habits echo through time. Sirius also gives us a chance to see how stars change color with heat. We often picture stars as white or yellow, but their colors tell us their temperature. Sirius leans blue, a sign of its intensity. It is a reminder that starlight carries messages in wavelength, not just brightness. When you look at its cold white-blue shine, you are seeing energy tuned like a tight string, no loose softness in its spectrum. Billions of years from now, another species in another time might see it differently, a cooled remnant floating quietly in the dark. But today for us, it is fierce and young. It is easy to think of stars as eternal, but in truth we are catching them at moments, never the whole life story. We look up and see a snapshot, not the whole film. Stars like these remind us of the raw power shaping galaxies. They light up gas clouds, carve cavities in nebulae, send shockwaves that spark new starbirth. They are the hammer strikes in the workshop of the universe. Without fast, fierce stars, the galaxy would be quieter, slower, perhaps too still for the heavy elements needed to build planets like Earth. Iron, calcium, carbon, oxygen, much of it born in massive stars that burned bright and died hard. Sirius is not massive enough to explode in a supernova, but it carries the flavor of that same family. Stars that do not whisper, but roar. We orbit our sun, safe in a warm bubble of predictable light. When we look to Sirius, we look toward a different kind of cosmic life. We see energy without hesitation. We see youth in its rawest form. It may not cradle life, but it displays how varied stars can be and how each plays a part in the huge, slow, quiet work of shaping the universe. The mysterious past of Sirius B. Today, if you point a telescope at the Sirius system, the bright primary star overwhelms almost everything around it. The little white point beside it seems humble, nearly lost in the blaze. But that calm dot is a remnant of a past far more dramatic than the one its partner is living now. It is the elder of the pair, even though it looks smaller and quieter. It has already lived through the kind of life Sirius A is only beginning to approach. In a sense, Sirius B is the faded echo of a cosmic firework. Long ago, it was the more powerful of the two, a star bigger than our Sun, burning with a heat and brightness that would have dwarfed Sirius A's current shine. But stars that are born with great mass often pay a price for that gift. When their fuel runs low, they cannot simply settle into a calm retirement. They break apart inside, layers collapsing and shedding until only a dense core remains. That is what we see in Sirius B now, the compressed heart of a once proud star. To us, it shines faintly, but this faintness is misleading. Up close, its surface is blistering hot. Its light is sharp, like the edge of a knife, not wide and warm like a campfire, but tight and intense. If you could float near it, you would feel a strong pull downward, even though it is only about the size of Earth. A teaspoon of its matter would weigh tons. Gravity has squeezed everything inside it into a dense memory of its former self. Astronomers did not always know how to read this story. When Sirius B was first detected by Alvan Clark in 1862, it seemed puzzling. Why would a tiny, faint star tug so strongly on Sirius A? That invisible pull hinted at mass far beyond what its brightness suggested. For many years, scientists struggled to understand how something so dim could be so heavy. It felt wrong, almost like a trick. Light usually gives away power, yet here was a star that had lost its glow but kept its weight. Slowly, the idea of white dwarfs took shape. This was new territory. The universe, it turned out, had layers that human eyes could not read on their own. White dwarfs are like cosmic bones, the strong remains of earlier lives. And in studying Sirius B, astronomers got one of their first real chances to see this concept in action. They learned that not all stars die in fire and explosion. Some collapse inward and hold steady, locked in a dense state where atoms are squeezed until they cannot be squeezed further. That pressure comes not from heat, but from the rules of matter itself, a kind of quantum crowding that says, no more room. Imagine a star swelling and swelling, layers drifting outward like breath from lungs too full until they float away as dust and gas. Imagine a glowing shell in space, and in the center, the core shrinking, tightening, fighting against collapse. In the end, that core becomes Sirius B. It is quiet now, but the silence carries the weight of a life that once roared. It is a survivor of its own fury. The changes Sirius B went through also reached Sirius A. When a star sheds mass, it changes its pull on objects around it. The orbit between these two stars widened over time, drifting like a rope loosening between climbers as one loses weight. Their dance stretches across centuries, but that stretch has shifted. Today, we see the system settled, but long ago its gravity field was different. Sirius B's transformation altered the future path of its younger companion, even if Sirius A does not show it in daily life. Space often hides change in slow motions. White dwarfs cool over time, and Sirius B is doing just that. Slowly, its heat leaks outward. It will dim further across millions of years, the way embers fade after glowing so brightly in a fireplace. But embers can still burn your fingers. Even in this late stage, Sirius B carries enough heat to outshine entire worlds. It simply does not spread that heat far. It keeps its stories close, tight in its tiny form. We sometimes think of stars as symbols of eternity. Sirius B breaks that image, showing that even stars have endings, and endings can be quiet instead of explosive. Yet this quiet is not empty. It teaches that the universe holds many ways to finish a life. Not all stars go out with a bang. Some settle softly into the night, still glowing, holding on to the last threads of their heat. In a way, Sirius B lets us peer into a future. Our sun will never become a white dwarf as massive as Sirius B, but one day it will also shrink into a dense remnant. It will glow faintly, not as a beacon, but as a relic, a final stage of life. Looking at Sirius B is like glimpsing a far future version of a familiar story, told in a different tone. Around Sirius B, no planets likely survived its wild past. When it swelled into a giant, any nearby worlds would have been swept up or burned. If anything once orbited close, it may now be dust drifting through space or fragments caught in the gravity of the main star. A planetary graveyard may circle that quiet core, pieces of a lost system. We cannot see them clearly yet, but imagination fills the dark with shapes of broken or forgotten worlds. In the silence of the Sirius system, there might be ruins we will never touch. As we look at pictures and measurements of Sirius B, it feels strange to think that this tiny point once lit space with a power far greater than its companion. Now Sirius A steals the spotlight, blazing bright in our winter sky, while Sirius B watches from the side like an older sibling who knows more but speaks less. If the universe had a library, Sirius B would be one of the books with thick, worn pages, small, heavy, full of history. Astronomy often reveals stories like this, where the great and loud eventually become small and quiet. Stars are not just objects, they are time capsules. Sirius B holds millions of years inside it, pressed tight by gravity, waiting for those who learn how to read light and motion and mass. Sometimes the faintest things carry the deepest past. Procyon, a star aging with quiet grace. Procyon sits only about 11 light-years away. Ancient skywatchers knew it, sailors followed it, and calendars once aligned to its rising. Yet for most of that history, no one knew that Procyon has a hidden companion, much like Sirius does. And just like Sirius B, this companion is a white dwarf, Procyon B. It is faint, tiny, and incredibly dense. But the dynamic between these stars is different. Where Sirius and its companion feel like a story of a wild youth and a quiet elder, Procyon feels like a slower play. The changes here come with gentler timing and long pauses between acts. Procyon A, the main star, is slightly larger than the Sun, not by much, but enough that its life will move faster. It has already grown warmer and more swollen than it was in its youth. Inside, its core has shifted to new forms of fusion, and its outer layers have expanded ever so slightly. It is not a giant yet, but it is on the path toward becoming one. If our Sun is still in the calm morning of its life, Procyon is walking into the afternoon. To the casual observer, nothing seems urgent. Procyon still gives steady light and looks healthy in every way a star can look healthy. But deep inside, time is ticking. One day, far in the future, Procyon will swell into a red giant, shedding layers into space and marking the end of its current form. It will not do this violently. It does not have the mass to explode in a supernova. It will fade and change softly, letting go of pieces of itself into the surrounding dark. A cloud of gas may form around it, lit from within by a shrinking core. And when the last outer layer drifts away, what remains will be another white dwarf, a partner to the one already there. Procyon B is faint, so faint that it went unseen for centuries. For a long time, astronomers only suspected its presence because Procyon A wobbled in its motion, the same way Sirius A does. When the companion was finally spotted in the late 1800s, it appeared as a dim spark, easily lost in the glow of the larger star. But that spark carried a deep truth about stellar life cycles. Like Sirius B, it had lived fast and finished early. It did not leave behind a dramatic imprint or a fierce change in its system. Instead, it settled into its white dwarf phase with little sign of distress. If Sirius B feels like a fallen giant, Procyon B feels like an elder who simply stepped off the stage when the time came. It still pulls on its companion through gravity, guiding its orbit over decades. The two stars move together through space like steady travelers linked by invisible thread. Comparing Sirius and Procyon reveals how stars can share similar origins yet age in different ways. Sirius is flash and speed, brightness and sudden turns. Its white dwarf companion is a remnant of high drama. Procyon, by contrast, ages like a poem read slowly, line by line, with meaning accumulating over time. Its main star is already expanding gently, and one day it will pass through a quiet transformation. Its companion stands as a reminder of what is to come, like a small window into Procyon's future. Even though Procyon A is brighter than the Sun, it is far calmer than the flare-driven red dwarfs we have met. It does not blast space with sudden storms. It does not toss energy in wild bursts. Instead, it radiates steady warmth. If life were to grow near such a star, it might have long, peaceful stretches of stable light. Planets in the right zone could enjoy conditions like those on Earth, at least until the star begins its slow expansion. The danger here is not sudden destruction, but slow change. Over millions of years, temperatures would shift, climates would drift, and habitability would move outward, like rings spreading from a pebble dropped in water. Astronomers have searched for planets around Procyon, hoping to find worlds warmed by such gentle sunlight. So far, nothing certain has emerged. It may be that planets once circled both stars, but did not survive earlier phases of evolution. Or they may simply be too small for us to detect with our current tools. The search continues because Procyon's calm nature makes it a compelling target. White dwarfs like Procyon B are not warm memories only. They tell us that even after a star ends its bright stage, it continues to shape the space around it. Slowly, Procyon B cools. Slowly, it releases the last of its stored heat. One day, so far in the future that human imagination struggles to reach it, it will become a cold ember, a black dwarf. But by then, the galaxy itself may have changed in ways we cannot guess. For now, it shines faintly and quietly beside its partner, marking time in a way only stars can. The unseen neighbors, brown dwarfs and rogue worlds. In the darkness between stars, there are neighbors we barely see. They do not shine like the sun. They do not glitter like Sirius. They sit in the quiet lanes of space like travelers who blew out their lantern long ago and now walk by feeling the ground instead of watching the path. These are brown dwarfs and rogue planets. They are the almost stars and the unsheltered worlds, the quiet population of objects that move around our region of the galaxy without ever calling attention to themselves. For a long time, astronomers suspected such wanderers existed. The early skywatchers looked for bright things because bright things are easy to find. Light reaches us like a shout across a valley, but these faint worlds whisper. Their voices fall short. For most of human history, they were lost in the black. Today we know better. We know the night is not empty between the stars. It is populated by dim bodies that formed like stars but never grew strong enough to ignite steady nuclear fire, or planets that formed near stars and then lost their anchor. They drift freely, like leaves pulled from a branch and carried away by a slow and endless wind. Brown dwarfs were once nicknamed failed stars. That phrase sounds harsh, as if nature tried and came up short. A better way to see them is this. Brown dwarfs are stars that chose a different destiny. They sit in a space between the true stars and the giant planets. They are not big enough to sustain the same burning heat as the Sun. They glow faintly, mostly in infrared, shining like the last warmth left in a cooling ember. If a star is a blazing furnace, a brown dwarf is a stone fireplace in which the wood never fully caught but still smoulders quietly. Our nearest known brown dwarf neighbours, discovered only in 2013, are Lumen 16A and Lumen 16B. They sit just over 6 light-years away, south of Alpha Centauri. For all that time, they were right there, tucked into the cosmic backyard, yet hidden. The discovery felt like learning that you had 2 silent neighbours living behind the trees at the edge of your yard for decades, making no noise, never turning on a porch light. They did not announce themselves. We had to build eyes sensitive enough to see their warmth instead of their brightness. These 2 objects dance around each other in slow orbits, locked together like partners in a calm, ancient waltz. They are cool by stellar standards, around a few hundred degrees Celsius on the surface, nowhere close to the scorching energy of a sun-like star. Yet they are not dead. Their atmospheres shift, churn and boil. Clouds likely form there, not of water but of strange minerals and molten vapors. Their weather patterns move in silence. Telescopes have watched their brightness change over hours, hinting at storm belts and spinning cloud layers. They are quiet, but not still. Brown dwarfs offer clues about the early lives of stars and planets. Once, we thought the universe made only stars and planets as separate categories. One burns, one does not. But brown dwarfs sit in between, showing us that nature likes gradients, not sharp borders. The gas and dust that collapse into stars can sometimes form a body just shy of ignition. It is like watching someone almost strike a match, seeing the spark jump, but the flame never quite catches. Yet the spark remains, glowing in the dark. Rogue planets tell another story. If brown dwarfs are the lonely siblings of stars, rogue worlds are the orphans of planets. They once circled a star, bathed in light and gravity, but something happened. Perhaps a close pass by another planet, or the tug-of-war of a chaotic young system, flung them away. Without a sun, they drift. Space becomes their only sky. There is no sunrise for them, no steady day, only eternal night, broken perhaps by faint starlight from afar. It might seem strange to imagine a world with no star. How could such a planet hold on to heat, yet some of them do? Giant rogue planets could hold warmth deep inside, like the Earth does, but stronger. They might have thick layers of ice above oceans of dark water. On the sea floor, volcanic vents could bubble and feed ecosystems like the ones near deep ocean ridges here at home. Life in the dark is not a fantasy. On Earth, creatures thrive in blindness, guided by chemicals instead of sunlight. So rogue planets raise a curious idea. Life might not need a sun at all. It might only need shelter, chemistry, and time. Astronomers have found hints of these free-floating worlds through gravity lensing events, where a hidden object passes in front of a background star and bends its light. The star brightens for a moment and then dims again, like someone stepping in front of a lamp in a distant room. Some events are too short and sharp to be caused by stars. They fit worlds the size of Jupiter or smaller. They move unseen, but their gravity leaves fingerprints on the sky. Brown dwarfs and rogue planets add a touch of mystery to our neighborhood. Even now, there may be hidden objects slipping through the dark close to us, waiting for the right instrument to reveal them. It is like living in a town at night, knowing there are quiet figures walking near the edge of the streetlights, their footsteps soft on the pavement. Studying these dim neighbors gives us a sense of scale. We often think of the universe as a place of bright stars and worlds spinning in warm orbits. But the truth is much stranger and more subtle. Shadows hold worlds. The galaxy is not only made of glowing suns, but also of muted bodies drifting without ceremony. As we build better telescopes, ones that can see heat instead of light or catch faint gravity ripples in the distance, we begin to reveal the quiet majority. Brown dwarfs might be almost as common as stars. Rogue planets may number in the trillions across our galaxy, like pebbles scattered across a desert floor. We are only now learning how big the desert really is. When astronomers finally saw Lumen 16, it felt almost like discovering footprints in fresh snow right outside the door. That moment changed how we look at our own cosmic neighborhood. It taught us that discovery does not always mean chasing the brightest beacon. Sometimes it means learning to listen to the softest whisper. The space near our sun is not a blazing sea of light. It is a quiet field with bright flowers scattered among deep, cool stones. We once thought the stones did not matter. Now we see they hold their own stories, carved over billions of years. They wait in the dark, not as failures but as reminders that the universe does not judge success by brightness. In time, little probes might drift close to a brown dwarf and taste its winds. Robots might land on a rogue planet, drilling through ice to find dark oceans below. Humanity could learn how life survives without sunlight, how worlds keep warmth locked inside like a secret hearth. Maybe our first meeting with alien life will not come from a sunlit planet like ours. Maybe it will come from a drifting world that forgot what dawn feels like. The hunt for planets around dim and quiet stars. Our eyes favor the bright ones. Sirius, Procyon, Vega, the sparkling names. But brightness is not a sign of calm. Hot stars live fast and burn out. They are like loud fireworks. Beautiful for a moment, but not a good place for something delicate to grow. Life, at least as we understand it, might prefer gentle warmth. Small stars, the dim red dwarfs and soft yellow dwarfs, can burn for billions upon billions of years. Some will outlive all other stars in the universe. They are patient. They sip their fuel instead of gulps. They shine quietly, like lanterns in a fog. If life is common, it might gather around these lasting embers. But there is a problem. Quiet stars are hard to read. Their light comes in thin threads, not bold strokes. To find planets around them, we must become listeners of whispers. It is not enough to scan the sky and look for sparks. We need instruments that look for tiny clues. A small dip in brightness when a planet crosses in front. A tiny wobble when a planet's gravity pulls on its star. A small twitch in color as light bends and shifts. Imagine holding a string and feeling the faintest tug from a child pulling at the other end. That is what astronomers face. The stars we hope to study are faint even to our best telescopes. Many of them flicker from natural activity, which can look like a false signal. Their brightness dances and their surface storms can trick us. Finding planets around them means sorting real signals from noise. Yet we keep trying. New tools are changing the hunt. Telescopes tuned to infrared light are opening windows into the dim star world because these stars shine more brightly in warmth than in visible color. Instruments on the ground and in space now watch thousands of faint stars at once. They measure light in careful steps, counting changes smaller than the blink of a firefly. Computers compare those changes to patterns we expect if a planet passes in front of its star. It is painstaking work, and often the first clue is only a hint, a suggestion. Months later, another slight dip appears, then another. Slowly, a rhythm shows up. A world reveals itself by repeating its shadow. Finding planets around dim stars is like learning to read the smallest handwriting. It teaches patience. It rewards those who return again and again, waiting for the right moment. Some stars have planets that orbit very close, so their dips happen often. Others may hold planets farther out, where years pass between each crossing. If Earth orbited a faint dwarf, it might take decades to notice its transit signals. Our search has only just begun. With careful instruments, the shift in starlight from gravitational wobbles can be measured. It is not easy. Stars flicker, clouds blur, instruments shake, and the tilt of a star's spin can hide the tug. But improvements in technology have begun to find these small wobbles even for faint suns. Quiet stars offer another advantage. Their steady nature makes life more likely. Around such stars, even planets with weak atmospheres might survive. Oceans could remain liquid. Air could remain clear. Life could stretch slowly, learning to sing over long ages without fear of sudden disaster. But there is tension here. While dim stars live long, many also flare violently in youth. So the best homes may be worlds around quiet stars farther along in age, those that have grown calm after their wild youth. But those stars grow even dimmer over time, making the search harder. It is like waiting for a bird to land on a tree at dusk, just when shadows start to stretch long and details fade. The stars most likely to hold life are the ones that hide their planets best. It feels like nature's test, a puzzle set before us. To see the small, we must build eyes sharper than ever. We must train ourselves to value faintness, not brightness. Astronomers who once chased grand light now chase tiny shadows. When the Kepler spacecraft first began watching stars, many were faint targets. It stared at them for years, waiting for small dips. The mission taught us that planets are common, even around dim suns. Now new missions like TESS scan almost the whole sky, capturing worlds around nearby stars we can follow up on. Future missions may block starlight so we can see the faint glow of planets directly, like shading your eyes with a hand to notice fireflies in tall grass. Ground-based observatories have also sharpened their tools, reaching levels once thought impossible. They listen to the subtle beat of star signals through the atmosphere, like hearing a whisper through a windy door. Together, these efforts form a kind of long-term patience. It is not a race, it is a slow unveiling. For now, every planet we find around a quiet star feels like a lantern lit on a dark shoreline. Each one makes us wonder whether we are looking at a world of clouds and rain, or a rock of bare stone, or a globe with seas that curl around continents. We do not know what colors their skies hold, or whether their nights have moons, or whether life stirs in their oceans like tiny sparks. But we look anyway, trusting that faintness does not mean emptiness. The next great discovery may not come from a blazing giant, but from a tiny star whispering around the edges of darkness, holding tight to a world that has waited for our eyes to grow patient enough to notice it. Future telescopes that will peer into nearby star systems. Today we stand on a ridge, looking across a valley of stars, knowing there are worlds on the other side but unable to see them clearly. We have hints, we have shadows, we have gentle tilts in starlight and faint dips that tell us something is there. But soon we will have tools that do not only listen to whispers. They will look directly into the faces of other worlds. They will peel back the glare of stars and reveal what orbits beside them. The idea feels unreal, like trying to believe that you will one day step inside a dream you can only picture through fog. Yet, these machines are not fantasy. They are designs waiting for launch windows, instruments planned with careful patience. Names like Luvoir and Habex float through research papers and dreams of scientists. Behind each name is a hope to see planets not as numbers or flickers, but as surfaces, atmospheres, places. Luvoir, the large ultraviolet optical infrared surveyor, is drawn like a giant eye in the void. In some plans, it stretches wider than any telescope we have ever put in space, its mirror a many-petaled flower of gold. If it flies, it will be a sharper eye than Hubble, stronger than JWST, able to see faint worlds near bright stars by blocking starlight with a perfect shield. That shield might float nearby like a giant sunflower in space, holding still in a delicate dance, aligning itself so that no stray ray escapes around its edges. The starshade idea feels like something out of a clever fable, a trick that uses darkness to find light. Habex, the habitable exoplanet observatory, is another dream rising from blueprints. It is smaller than Luvoir, but more focused, like a magnifying glass held steady over a narrow field. It will not look everywhere. It will look at the few stars most likely to hold Earth-like worlds. It could use its own starshade too, a blocking disk bigger than a football stadium, flying thousands of kilometers away, staying so precisely aligned that the telescope behind it sees the glow of a planet next to a star as bright as a lighthouse. This is like trying to spot a firefly next to the beam of a searchlight from thousands of miles away. Yet the physics says it can work. The engineers believe they can build it. The thought of seeing another Earth-like world not as a guess but as a globe is almost too large to sit still in the mind. Picture looking at a pale blue dot around Alpha Centauri and seeing clouds in an alien sky. Imagine measuring the thickness of its air, the role of its weather, tiny changes in shade as seasons pass. It could feel like watching a little Earth across the cosmic pond, a cousin drifting in sunlight. And then the deeper wonder rises. What if we see signs of life, not cities or lights, but chemical whispers in the air? Oxygen paired with methane, a strange balance of gases that should not exist without something breathing or growing beneath the sky. These future telescopes will not search alone. On Earth, giant observatories will lift their own eyes. The extremely large telescope in Chile, with its wide mirror, will study nearby worlds with the sharpness of a mountain hawk. It will pull apart starlight into clean colors and read the faint fingerprints of molecules. It will feel for water vapor, carbon dioxide, ozone, and maybe even the faint breath of something living. The 30-meter telescope, if completed, will join this watch. The giant Magellan telescope, with mirrors arranged like petals, will sharpen every image, squeezing as much detail as possible from the faint size of distant planets. Together, these ground giants will act like scouts for the great space missions that follow. But even these huge mirrors have limits. They look through Earth's air, and air wobbles. Though adaptive optics correct some of this, space remains the cleanest place to see clearly. So Luvoir and Habex stand like future sentinels in orbit, waiting for approval, waiting for the will to build them. Their designs sit in computer models and long reports where diagrams glow like lanterns guiding the future. Their creators imagine launch fairings opening like petals in sunlight, mirrors unfolding into delicate symmetry, starshades gliding into place with gentle pushes from thrusters. Once they are ready, these telescopes will spend years staring, planet by planet, system by system. They will gather light like dust drifting into cupped hands. They will hold each photon and turn it into data, into color, into graphs that rise like hills and fall like valleys, showing the contents of alien skies. They might even capture time-lapse images, watching clouds slide across a world, or ice caps shift, or storms roll across oceans never seen by living eyes. It might seem slow, a year spent staring at one star, another year for the next. But the universe waits, so we can too. When the first images arrive, they will be quiet, not fireworks. Science usually speaks in soft tones, but the meaning will not be soft. It will be like learning for the first time that a far-off mountain range hidden by mist is not empty, but full of forests and rivers. We will realize that the sky we grew up with, the one that looked like glitter on black velvet, was not decoration, it was depth, it was geography. Some future missions may go even further. Concepts like the Life-Finder telescope and even more distant dreams like kilometer-scale structures in orbit shimmer at the edge of imagination. These are not projects yet. They are wishes given shape in diagrams and thought experiments. But every great tool began as a sketch. Someone once drew Hubble. Someone once scribbled the first plans for JWST on a pad. Now they float in space. What lies ahead feels like the slow rising of dawn. We have already seen silhouettes, gas giants with striped storms, hot worlds that glow in infrared, young planets still warm from birth. Soon we may see temperate rocky worlds, the true prizes. When Luvoir or Habex looks at Alpha Centauri or Tau Ceti or nearby red dwarfs, we might finally see what their worlds truly are. Dry rock, frozen plains, ocean-covered spheres, cloud-wrapped mysteries. Or maybe one day something stranger, something with colors we do not have names for, something alive in the quiet pulse of chemistry and chance. The tools are coming, the patience is already here, and the longing to see, to really see, has never gone away. It has simply waited for mirrors large enough, instruments quiet enough, minds steady enough, and hearts brave enough to step closer to the truth that has always hovered just beyond our sight. We are not only observers of the stars. We are participants in the story they tell. Soon we will turn a page, and the worlds next door will no longer be rumors. They will be seen, steady and real, floating in the soft glow of their suns, waiting for us to learn their names. Direct imaging dreams, seeing alien worlds in detail. In the quiet space between stars, another dream waits. It is simple to say, yet hard to believe. We want to see other worlds with our own eyes, not as dots, not as lines in a graph, real pictures, real shapes, planets shining in reflected light, maybe with oceans glimmering or clouds rolling across their skies. It sounds like something a child might sketch on notebook paper while staring at the night. But this dream is not childish. It is one of the most serious and ambitious goals science has ever held. Right now, even the closest exoplanets are invisible to us as landscapes. They are hidden in the bright glare of their stars, washed out like a firefly sitting beside a lighthouse. To look at one, we need to block the light of its star without blocking the planet itself. This is where the idea of coronagraphs comes in. A coronagraph is a tool built into a telescope to hide a star. Inside a future telescope, a small shield sits in the path of the starlight. It blocks the center beam and uses careful optics to cancel stray rays around the edges. It has to be perfect. Even tiny imperfections could scatter light like dust on glass and smear the image. This challenge is like trying to stop ocean waves with a thin line drawn in the sand. Yet engineers believe they can control light at this delicate level. Step by step, they are building machines that can hold a beam still, smooth it and cut the glare down enough to reveal faint worlds. Still, coronagraphs have limits. So another idea rises from the pages of plans: the starshade. A starshade is bold in a different way. Instead of sitting inside the telescope, it flies in space as a distant partner, thousands of kilometers ahead. It is a huge flat shape, built like a black metal flower with many petals. Its edges are carved like long pointed leaves, each one shaped to control how light bends. From far away, this shape casts a small shadow. The telescope waits inside that shadow. In that darkness, the planet's light can finally shine through. Engineers have practiced folding starshade petals like giant origami. They have tested how to push and steer such a thin machine without letting it wobble. The petals unfurl in computer models like wings. If launched, they would unfold in space, opening like a steel flower built for the void. The telescope behind would wait in quiet shadow, holding its breath as a planet finally appears. The first images may be faint at first. A small pale dot, a tiny half-moon shape, maybe a smooth glow. It will not be like stepping onto a new world. It will be like spotting land across a sea after months of sailing. Detail comes later. The first pictures are proof. They say, there it is. They give shape to something we only guessed. They turn a world from a maybe into a fact. Over time, technology will sharpen our eyes. Today, we imagine the first generation of direct images as rough maps. But we also know how science grows. Think of the first photos of Earth from space. Grainy, tiny, hard to believe. Now we have satellite views so sharp we can see shadows of trees. The same will happen with exoplanets. The first picture might look like a soft ball of light. Later, we may see cloud bands. After that, storms, oceans, polar caps. The soft blue curve of a world with water, or the red rust of a desert giant, or a strange glowing haze that hints at life in forms unlike ours. To reach those futures, each step must be taken with patience. Scientists test coronagraphs in labs, shining lasers through tiny masks and mirrors, shaping beams into clean circles. They check vibrations, heat changes, how materials bend under stress. They build starshade models in warehouses and fire lasers to measure how light diffracts around their edges. In these rooms, the future looks like wires, mirrors, metal petals and charts. It does not look like alien oceans yet, but every careful adjustment moves us closer. Beyond starshades and coronagraphs, other ideas also whisper from the horizon: interferometers, which combine light from many telescopes to act like one giant mirror. Giant space mirrors that unfold like silver umbrellas. Thin film lenses kilometers wide, floating like sails in space. Each idea is like a seed that may grow later, once we prove the first ones work. Science is often cautious, but imagination stands behind it like wind at a sail, pushing just enough to move forward. The real power of direct imaging lies not only in pictures, it lies in what follows them. Once we can separate a planet's light from its star, we can study that light. We can pull it apart into a rainbow of colors and read it like a fingerprint. Every gas in a planet's air leaves its mark in that rainbow. These clues could tell us not only whether a world has seas or clouds, but whether life may be shaping its air. Picture seeing the faint glow of a distant Earth-like planet through a star shade. Then imagine measuring its light and finding oxygen. On Earth, oxygen is not stable without life. Plants breathe it out. In oceans, tiny plankton release it. It builds in our sky only because life keeps making more. If we saw that on another planet, even faintly, it would be a quiet shock. A moment when two simple lines on a graph whisper that we may not be alone. Some exoplanets may be easy to see. Some may hide in glare too strong for even our best tools. Some might be worlds with no air, no water, no comfort. Others may be covered in clouds and mystery, but each view will teach us. Even a barren rock tells a story. Even a lifeless desert helps us understand where life can grow and where it cannot. One day, direct imaging could go beyond nearby stars. We might stare at worlds dozens or hundreds of light years away, not just our local neighborhood. We might see planets orbiting stars we can barely name today, and each one will pull at our curiosity like a tide. Somewhere in that long line of worlds, one may show a signal so strong and clear that there is no doubt. And when that happens, whether in 50 years or 100, the view will not feel like looking outward. It will feel like looking across, like waving at someone far away, across a field, knowing they stand on their own ground, under their own sky, living their own life under a star that warms them as our sun warms us. For now, the dream waits in quiet metal parts, folded designs and computer models. But it is coming. The first face of another world will appear, and it will change not only science, but us. It will remind us that sight is not only a human sense, it is a human hunger. To look is to wonder. And soon, for the first time in all of history, we will look across space and see a world that has never seen us, shining gently in the dark, and know it is real. Star-chasing probes, will we ever send one? When people first whispered about interstellar travel, it sounded like a fairy tale dressed in math. Starships buzzing out of the solar system and shooting toward Alpha Centauri like arrows. Whole colonies in hibernation. Vast engines roaring in the dark. But when scientists sat down with actual numbers, they found speed was not the hard part. Energy was. Every tiny increase in velocity demanded a mountain of fuel. And the faster you push, the louder physics laughs. If you want a ship to go even a decent fraction of light speed, you face demands that feel almost unreasonable. Rockets become fuel tanks with tiny cabins. Nuclear drives become giant flying reactors. Everything becomes too heavy, too risky, too hot, too expensive. Then someone had a stranger idea. What if you do not bring fuel at all? What if you let light push you? A light sail sounds like it belongs in fantasy, but the idea is quiet and simple. Light carries momentum. If you stretch a thin sheet in space and shine a strong beam on it, it moves. Not fast at first, but steadily, like a leaf blown across water by a constant gentle breeze. Over time, the speed grows. With no fuel to run out, you just keep going. This idea became the seed for breakthrough Starshot. Instead of one big spaceship, send thousands of tiny ones, each one about as heavy as a paperclip, each one riding a sail as thin as a thought. Use powerful ground-based lasers to push them to 20% of the speed of light. If everything works, these tiny probes would coast to Alpha Centauri in about 20 years. Not centuries, 20 years. For the first time, you could imagine seeing another star system within a single human lifetime. At that speed, space becomes a wind tunnel of deadly dust and radiation. A single grain of sand would be a bullet. But there is a sense that danger cannot stop every dream. These probes would be small and armored in clever ways. They would not carry people, only sensors. Their message back would be faint, like a voice calling across mountains. But if even one survived, it could send pictures. Actual images from another world around another star, a tiny visitor crossing the ocean between suns. Still, this plan lives mostly on paper. The lasers needed would be unlike anything we have ever built. The materials for the sails must be light and strong in ways we have not yet mastered. The electronics must endure decades in space while staying smaller than a fingernail. Even if humanity builds all of this, there are problems we cannot avoid, keeping a laser perfectly pointed across thousands of kilometers, surviving micrometeor strikes, communicating from a distance 4 light-years away with a transmitter the size of a grain of rice. Every part of the challenge feels like a locked door. But each door also has a key waiting to be made. Long before Starshot, other interstellar probe ideas came and went like comets in the night sky of imagination. Project Daedalus dreamed of fusion engines, swallowing helium-3 like cosmic fuel and flying to Barnard's star in 50 years. Orion thought bigger and stranger, using nuclear bombs kicked out behind the ship like firecrackers. A ride powered by explosions. Even now, those plans feel like a dare whispered into history. Too wild, too dangerous. Those early concepts raced ahead of their time. Today, we can only run our fingers along their blueprints and wonder how long it will take before the world gains the strength to build such things. The truth sits quietly between hope and patience. Physics never promised us starflight. It only promised possibility wrapped in difficulty. Even if we push forward, the journey to another star would be a silent trial, a ship drifting through a lightless nothing where nothing helps you and nothing saves you. Starspace is not like our solar system. There is no radio support network, no energy to grab, no helpful planets to swing around. It is a marathon across a desert with no water and no shade. If a probe dies halfway, there is no rescue. It becomes a frozen pebble, drifting forever. There is no reward waiting for the probe itself, only for the minds who dreamed it and the eyes that will one day see its pictures. It is pure exploration. No gold, no land, no conquerors. Just curiosity stretching its arms. When you zoom out, our star-chasing ambitions look like a child trying to touch the moon by climbing a tree. But trees lead to rooftops. Rooftops lead to mountains. Mountains lead to rockets. Each step might feel small, but each one lifts us higher. To send a probe to another star, we must shrink our tools, sharpen our lasers, toughen our materials, and learn patience for journeys that outlast careers. We also must accept that some missions will vanish into the dark without reply. In that long view, interstellar travel is not just engineering. It is an act of faith. Faith that the universe is worth reaching toward. Faith that even if we move slowly, the stars will wait. Faith that humanity will last long enough to see results. Sometimes we imagine a future where starships are common, sleek vessels gliding like silver nerves through the dark, entire generations born under artificial skies. But the path to that future likely starts with one tiny probe, smaller than a hand, carried by light and hope. If it reaches Alpha Centauri and sends back even a single pixel, one tiny dot showing a real world around another sun, that dot would be enough to change how we see our place. It would say, we did not only dream, we stepped, we tried. We crossed the first grain of the cosmic beach. Plenty of ventures in history began with something fragile. The first airplane hops, the first telegraph clicks, the first human who looked at the ocean and wondered what lay beyond. At that moment, they had no proof of islands or continents, only curiosity strong enough to push a boat into water wider than courage. We sit on a similar shore now. The stars are the far horizon. Our boats are ideas made of math, lasers and thin sails. Somewhere out there, Alpha Centauri glows like a distant lighthouse. We do not know when the first probe will launch, but when it does, it will feel quiet and strange. No roar, no cheering blast-off, just light pushing a wafer into the dark. A soft beginning for a long journey, a small spark sent ahead to scout the path our species has only traced in stories. For now, we plan, we build, we test, we argue, we dream. In labs and meeting rooms, people curve their hands around cups of cold coffee while staring at screens full of equations and star charts. Outside those rooms, the night sky keeps shining, unaware of our plans. But we keep working anyway, like ants trying to read mountains. One day, if our tiny ship sends back a faint signal, and humanity listens to it together, even for a moment, we will feel something rare. As if the universe answered a whisper with a whisper. As if it said, "Yes, you may come closer." And so the dream continues, walking step by step toward the stars, steady, patient, and hopeful. The physics gate, breaking through interstellar time. Time is the real border in space, and it does not move even when we stand there and beg. Distance gets all the attention, but time is the heavier lock. If space is a giant field, then time is the fence around it that never rusts. You can imagine engines strong enough to cross light years. You can imagine sails that drift like silver wings, and you can imagine sails pushed by lasers that hum like beehives in the dark. Yet none of those solve the quiet weight of years. To go to another star is not like going to another country, where you bring a passport and a lunch and expect to be home by night. It is like planting a tree in soil you may never walk on. The journey itself becomes a story you cannot finish in a single sitting. It stretches beyond personal pride and reaches into patience that might span generations. This makes interstellar travel feel less like a voyage and more like an agreement with the future. When we talk about rockets and sails and nuclear engines, we often forget that time does not bend just because we wish it to. Even at speeds beyond anything we have built, the years pile up like snow. Light is not only fast, it is a ruler for the cosmos. It defines what is possible. If you move at a tenth of light speed, you are still a child trying to chase a racing horse. A star 4 light years away becomes 40 years of travel. And that is only for the nearest one. Most stars sit far beyond reach, as if time itself wrapped them in locking rings. This is why interstellar travel feels almost like gardening on a cosmic scale. Plant seeds now, wait decades, maybe longer. The ship you send might age in the dark while new languages rise on Earth, while cities reshape, while technology changes so fast that the probe becomes a museum piece by the time it arrives. Imagine a phone from the 1980s trying to talk to a modern tower. Imagine that stretched across light years. That is the communication challenge between generations of machines, knowledge, and people. A mission to another star will not just test engines. It will test endurance. Not human strength in the muscle sense, but emotional and intellectual patience. To wait decades for a signal is to live with a quiet sort of faith. A belief that the universe pays attention and rewards those who keep trying. Engineers must design parts that do not just last years, but decades. Circuits must survive radiation long after their makers retire. Software must adapt without human hands. There is a sadness in that, like sending a message in a bottle into the sea and knowing you will never see who opens it. But that sadness has another side, a poetic side. When we plan missions that exceed one lifetime, we are admitting that humanity is bigger than any one of us. Our effort becomes a bridge for strangers who will live in futures we cannot imagine. The universe becomes something we do not conquer but share, across generations like a storybook passed from child to child. Still, time remains stubborn. Even missions inside our own solar system have felt the strain. The Voyager probes have been traveling for decades, and they are only now pushing into true interstellar space. Their signals are faint, shaky, like old voices speaking through dust. We celebrate them because they remind us of persistence. They show that machines can last longer than anyone expected. But between us and the stars sits not only space, but a clock that does not skip a beat. When we talk about breaking a physics gate, we often think of faster-than-light travel, warp drives, wormholes. But the real gate, the one right in front of us, is not a glowing tunnel or a hidden dimension. It is time itself, staring back without blinking. To pass through it, we do not need magic. We need patience. We need to build things that are loyal, stable, steady. We need to accept that some journeys will start with people who never see the ending. In this way, interstellar travel becomes a test of values as much as science. Do we act only for quick rewards? Or can we build monuments made not of stone, but of intention, endurance, and curiosity? It feels like a strange kind of bravery to build a mission knowing you will never read the final data file. But this is the shape of star travel. It is a candle lit for someone else to enjoy. The universe does not rush, and maybe we are learning to match its pace. Technology often grows in bursts, yet space travel teaches slow breathing. We live in a world where we refresh screens every few seconds, but reaching another sun may require waiting longer than most lives. That contrast asks us to think differently about progress. It asks us to see time not as an enemy, but as a partner. Inside laboratories, people work on microchips that can self-correct, on batteries that fade less, on coatings that shield against cosmic rays. These inventions feel small, humble. Yet they are the tools needed to survive long journeys. No hero cape, just quiet toughness. To cross time's gate, we do not need muscle. We need grit shaped into machines. Future missions might launch not once but in waves, like a flock of metal birds leaving Earth. Some may fall, some may break, some may vanish into silence, but a few may endure, and each one that does becomes a seed. We do not know which seed will sprout first. That is part of the story. Space exploration has always felt like a game, where the universe watches us fumble with keys, trying every one until something clicks. People often say that if we reach another star, we will become a true spacefaring species. Yet maybe the real transformation comes earlier, when we decide to act across time, not only across space. When we stop thinking of missions as events for a single generation and start seeing them as threads in a long cosmic tapestry. Once we do that, the stars stop being points of light and start becoming destinations in a slow, patient march. Somewhere, centuries from now, there may be children who grow up knowing that humanity has touched other systems, that tiny probes or quiet ships have traveled where no life from Earth has ever stepped. Maybe those children will stand under alien skies, their boots pressing into soil that once only existed in dreams. Or maybe they will simply watch new stars rise on screens, knowing that someone long ago believed in that moment enough to begin. Time is not a wall, it is a long hallway. We can walk it. We only need to choose to keep going, even when the steps are small and the end is not yet visible. The universe will not move toward us. If we want to meet it, we must lean forward, one quiet year at a time. A possible future where nearby stars become home. A future where nearby stars become home might start with machines, not people. Small probes drift outward, then smarter probes, then fleets of them, almost like flocks of iron birds moving through cosmic night. They carry sensors, cameras, simple logic. Later they carry factories no larger than a suitcase, programs to build tiny outposts on lonely rocks or moons around distant suns. Not outposts with people, but outposts with purpose. Relay stations, power collectors, data labs, calm in their solitude. These early steps are silent. Space expands its reach the way moss claims stone, slow, soft, and unstoppable once it starts. Maybe the first star to hold our presence is not Alpha Centauri, but a smaller, quieter system where the work feels easier, where dust rings are gentle and frozen worlds wait like blank pages. Machines can live where lungs cannot. They do not need sunlight the way we do. They only need steady power and well-made circuits. Over time, the machines become caretakers of future dreams. They turn raw rock into useful materials, collect energy from faint starlight, and slowly build safe points in the dark. And Earth watches from far away, knowing that what begins with robots may someday invite humans. We might not rush. We might learn from our solar system first, how to build habitats around moons, how to live in giant stations that circle gas giants like slow silver rings, how to harvest energy from quiet stars, how to recycle air and life until we become gardeners of our own world-made bubbles. By the time real human travel begins, those far-flung machine outposts could be ready, like homes warmed before guests arrive. The ships that carry people will not be fast. They will feel less like rockets and more like floating towns, sealed gardens gliding across starlight. Inside them, there will be children who never see Earth except as a memory in pictures, elders telling stories no one else remembers, gardens lit by artificial suns and corridors that echo with generations. Imagine life aboard one of these starships. Days filled with learning, working, farming, fixing, laughing, fighting, forgiving, and dreaming. A small world wrapped in metal, but alive with sound. People would grow up knowing their path is not a trip, but a life. They would look out through quiet viewing windows and see no flash of speed, only the slow movement of stars, like beads sliding across a string. The journey would shape culture, language, identity. We might stop thinking of space travel as leaving Earth and start seeing it as living in motion, forever in between where we came from and where we are heading. Then one day, far later than any launch crew expected, a ship arrives. A white star hangs ahead or a red one, glowing calm like a small ember in a black hearth. New worlds circle it, silent and untouched. The descendants who step forward into that new sunlight are not pioneers in capes. They are gardeners arriving at fresh soil. They are patient souls carrying the weight of a long journey, ready to build gentle roots in a place no human foot has touched. Maybe they do not land at first. Maybe they build stations in space, then rings, then slow, careful landings. They test air, soil, radiation, winds. They plant hardy plants from Earth, chosen not for looks but for survival. They craft small lakes, domes, shelters. In time, as decades pass, the place becomes familiar. A new sunrise becomes normal. A new sky becomes home. Children born there might see Earth not as their origin, but as a story, spoken softly like a bedtime tale carved from memory. And Earth itself continues on, a parent watching new branches grow. Communication between stars is slow, like letters carried by ocean ships in ancient times, but it is steady. Knowledge passes across the void in beams of radio light, patient and faithful. One world learns from another. Mistakes in one place teach caution in another. Breakthroughs travel back like gifts. Over many centuries, a network forms not in space but in time, a string of outposts, worlds, stations and starships all sharing one lineage. Humanity in such a future becomes a ripple spreading slowly, never rushed, powered not by engines but by endurance. And not every star becomes a home. Some are too wild, too bright, too violent. Some are quiet, slow, gentle. We gravitate to the peaceful ones, the warm ones, the ones whose light feels kind. In that silence, life grows in pockets. There may come a time when someone stands on a moon circling Alpha Centauri A, looking up at two suns and remembering an old story of a ship that left Earth centuries before they were born. They may live in a dome that breathes for them, or in a cave warmed by geothermal vents, or in a floating city in the system's outer space. And their view of the universe will feel natural, not strange. They might ask why their ancestors ever doubted the journey, the same way we now ask how explorers of oceans ever feared crossing the horizon. The stars near us are touched one by one, each step separated by generations, like stepping stones across a slow river. There is something peaceful about that vision, a future made not of sparks, but of glowing embers, carried carefully from one hearth to the next. It may not be fast enough for legends or flashy tales. It is slow and real. It is how mountains rise and how civilizations last. And there, around distant suns, our species might find not glory, but belonging. A quiet place in the endless dark, earned through patience and held with care, like a candle flame passed hand to hand across generations until the stars themselves become neighborhoods and home becomes a wide and gentle word, not tied to one world, but shared across many. How would you rate humanity's chances of achieving this future? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.